Okay, also Dr. Ahmed is joining. Assalamu alaikum, Dr. Ahmed. Yeah, you are just muted.
اوكي يا اهلا وسهلا.
اهلا دكتور احمد، منور.
مهندس ازي حضرتك؟
اهلا بحضرتك دكتور احمد، منور.
وحشني كتير انتوا الاثنين.
والله وحضرتك اكتر، منورنا.
ربنا يخليك.
ايه رايك يا باشمهندس؟ نبدا. دلوقتي هو ما فيش حد دخل معانا بيتكلم لغه غير العربيه، فانا بشوف المفروض ان في ناس هتيجي من اوروبا، بس ممكن it will take time. كده كده احنا هنسجله بقى بالانجليزي وخلاص. نبدا بال ماشي. اوكي
زي ما انتوا شايفين ما فيش فرق يعني.
تمام. is there anyone اوكي، هو مشكلة لو في ناس هيجوا بعد كده يدخلوا، فهي دي الفكرة. ويسرى معانا كمان عشان تفولو اب معانا اللي احنا بنقوله. اوكي. So welcome everyone to the 5th edition of the Quantum AI monthly series. Today we have a very distinguished speaker, the scientists and the experts from all over the world, and it happens to be the majority of them from Egypt. That's a good thing indeed. And Bibliotheca Alexandrina, and of course iQafé are organizing this series, and we are hosting a variety of topics related to high tech and also the quantum computing and the AI, to cover a variety of topics related to the industry. I'm sharing my screen now. Okay, so today we have very well-known and distinguished speakers covering a variety of topics related to the quantum computing and AI arena, and also related to high-performance computing and the larger-scale simulations. And the theme of today is machine learning and the quantum machine learning and quantum software optimization. And also we are featuring a nice talk about IBM ecosystem in Saudi Arabia, and also what IBM is offering for the quantum computing industry and ecosystem as well. So today we are going to start with a short introduction about the Alexandria Hackathon and the summer school that we are going to organize in the upcoming 2 months. And this will be followed by a talk by Professor Ahmed Shawqi Musa about larger scale simulations, high performance computing, and also the enabling the role of machine learning in these applications. And this is sort of will pave the way why we need machine learning, and potentially why also we need the quantum machine learning after. This talk will be followed by an idea about the quantum machine learning and why it's important for larger scale data sets. And then another talk by Dr. Muhammad Amin, that I think one line is missing here, for the classical machine learning role in chemistry and the biosciences. And this will be followed by a talk by Yusra Farhani about advances in quantum software for machine learning and optimization, and then Engine Ahmed Salim for the overview of the quantum software ecosystem in Saudi Arabia and at IBM. And this will be followed by question and answers. Okay, so yeah. So first, my name is Astar Salim, and I'm currently working as quantum education officer, but also lecturer and researcher at Amsterdam University of Applied Sciences, and also general manager of Molkit CEST, also a quantum computing startup based in France. And with that, I'm giving the floor to Engin Youssef to talk about the Alexandria Hackathon.
Thank you, Dr. Taha. I am Youssef Al-Lakar. I work for the Library of Alexandria, where I head the International School of Information Science. And our mission is to support research through technology. One thing is the high-performance computing service that we provide to universities and research institutions in Egypt. We started this journey with iQafé and Dr. Taha in December. This is the 5th edition. And since we started, we set for ourselves a milestone in September for the Alexandria Quantum Hackathon, which we are now 2 months away from this event. We look forward to it being something that will help the community build capacity and make connections and make networking and be serve as maybe a foundation for future similar events in Alexandria. For this event, we are the focus for the participants is to mainly be from Egypt, but also for the mentors, speakers, and judges to be from Egypt as well as from abroad. We expect funding for accommodation for the participants who are not from Alexandria, and also to support travel for mentors, speakers, and judges who will be coming from outside Egypt. We are, as I said, 2 months away from the hackathon, so our plans are becoming more concrete, and we welcome any questions. I think the easiest way is to post them on the WhatsApp group. I think maybe the next edition will have more details about the hackathon, the theme, the possible ideas for the teams. We are looking at, I think, 6 teams that will participate eventually in the hackathon. And before that, we also have plans for a tryout hackathon that Dr. Taha will have more information on. So I hope this will all be very useful to the community, and we look forward to it. And once again, many thanks to Dr. Taha, especially for continuing to lead these editions and this effort toward the hackathon. And also, thank you so much to our distinguished speakers that we've been having, including, of course, our excellent professors at many of Egypt's universities. And we're very grateful for your efforts, and we look forward to the rest of the journey. Thank you all.
Thanks very much, Mr. Yusuf, for this nice covering for the hackathon. So this is the website of the hackathon. Feel free to apply if you are also a student based in Egypt, and if you are a teacher or expert abroad, you would like to serve as a judge, either in person or in online, also feel free to reach out to Mr. Yusuf or to us. And we have potential projects related to summer schools, and the tryout hackathon that will be organized at the end of July. Okay, so William, hi. So you have a question, please go ahead.
Can you hear me?
Yes.
Yes.
Yeah, now.
Yeah, for people who like hackathons, myself and my esteemed colleague, Joe Reddix, from the Reddix group, are sponsoring a hackathon. It's going to be pretty unusual. It's going to be a 30-day hackathon, and it starts on October 3rd and ends 30 days later. And we plan to have cash prizes of $5,000 for first place, $3,000 for second place, and $1,000 for third place. And because the quantum community is so important to us, we decided to not make it US centric. We're opening this up to international registration. So for people who enjoy the Alexandria hackathon, please come join us for the hackathon we're sponsoring starting October 3rd.
Yeah, thanks very much, William, for the information about the hackathon. And feel free out, guys and girls, indeed, to apply to benefit from this beautiful hackathon organized by William and Joe Reddix. So now we are gonna move to our next speaker. I'm just sharing the screen again. So our next speaker is Professor Ahmed Shawqi Musa, and he's gonna talk about large-scale simulations and high-performance computing and the enabling role of machine learning in these applications. Dr. Ahmed was my tutor and also my teacher during my undergrad, and also served as a mentor for my whole academic career. So thanks very much for this. And Dr. Ahmed combines expertise from both academia and industry. So he's Associate Professor of Computing and Computational Sciences at Faculty of Computers and Artificial Intelligence at Cairo University, where he is also founder and the head of the HPC R&D lab. He also served as HPC director at the Applied Innovation Center of Ministry of Communications and Information Technology, where he founded and led the first HPC system at MCIT. Dr. Musa's main field of expertise is HPC and its integration with various AI paradigms to create computationally intelligent HPC systems in both the academic and industrial worlds. His academic achievements include contributing innovative applied solutions to improving HPC systems, performance, and solve scientific problems involving the modeling of larger scale, complex, dynamical, uncertain systems. In the industry, he led mega multidisciplinary, multi-sector applied projects from R&D to innovation using HPC, AI, and other emerging technologies. Dr. Musa holds a US patent, co-founded and led several national entities, and serves as expert consultant for many national and international institutions. So with this, I give just the floor to Dr. Ahmed.
Well, thank you for the introduction, Dr. Taha. I'm proud, actually, of being your professor at a certain point of my life. I'm proud of that. I'm very happy. I also want to add one point, that after I left MCIT, when I was the HPC director there, I'm now founder and managing director at Otimi Systems, a new startup company specialized in HPC and AI. That was officially, we had a soft launch a few years ago, but it was officially kicked off actually a month ago. So this is not on the biography yet.
So congratulations, Dr. Ahmed, for the nice new.
Thank you. It was a good start, and we fortunately, even before we officially kicked off, we had some a few but very significant business running out already in the field of HPC and AI consultancy, installation and design, running already right now. Let me see how I should, I think I can just share the entire screen and then select from. You should see my screen now, I suppose.
Yes, yeah, we see
Okay.
yeah, indeed.
Okay, I'm happy and proud to be asked to give a talk in this event. I am really proud and confident of the success of this series of talks. Very informative, educative, and a great work being done by the Bibliotheca Alexandrina and iQafé. I was asked actually this time to give like samples of use cases, case studies that I conducted myself in larger scale simulations. I've done many of those in different levels, in different fields. So it was not easy to select from. Then I finally decided to select a few and then give hints about some others to maybe talk about in the future, or to extend the collaboration with some of you esteemed professors and students in the future about it. Before I start talking the core talking, or the core of the speech, let me remind you of this. When we talked before about the fact that HPC is the vehicle on which AI rides, so it is the reason that we have AI now. But not only that, it actually transformed the practice of science and engineering altogether. In the old days, science was theoretical or experimental. And from the experimental part, the engineering part stemmed out to transform these experiments into something pre-designed and useful to solve a problem. The HPC actually led to expanding these paradigms from only theoretical and experimental into what we call today computational science. And I think we talked enough about that in previous talks. And we talked about many fields that are not easy to develop a theory for. So the practice of theoretical science in this case is very difficult, if not impossible. And also the experimental part of it may be not only difficult, but actually impossible. And we gave many examples of this. I think the audience who attended the previous talks know that very well by now. This actually led also to what we call today data-driven science. Computational science means that we have or we can construct a model. But we cannot develop a theory, and we cannot do physical experimentation. Actually, recently we have been dealing with sciences that we do not even have a computational model for. We do not have the model to build computationally. All we have is data. It can be unstructured, massive data, big data of all types of variety. We will refer to that in a few minutes from now. But almost impossible to build a model. Actually, building the model is the outcome of the practice. And this may sound strange at the beginning, but this is what we call data-driven science, where data is collected massively. It could be multidimensional. All types of uncertainty are available in this data, and we are required to use this data to do something. And this is what we call, again, data-driven science or data-driven engineering. All this is actually done by what we call large-scale simulations, which can be on different levels and in different types of application. It can be on the student's level to learn about something that you cannot demonstrate the physical experiment, but you can do it computationally. It can be on the scientific level to come up with new discoveries and predictions for new things. So you can use it on many levels, and I'll try in the available short time to give some of the examples that I personally did. There are also, of course, worldwide much better and much more complicated examples, but I will talk about my own experience in this case. The first case, let's call it case study 1. This was a research toward a dynamic IoT-based HPC system. This actually was a master thesis that I developed the topic for, but one of my previous students who was an excellent student did master thesis, and in my opinion, by the work she finished, she could have deserved a PhD, not only a master's degree, but she was in the master's program anyway. The idea of this thesis was as follows. We were at that time still in the search, and until now we are still in the search for stable exascale computing systems, very, very high performance computing system, exascale. And this was complicated by many things in science and engineering, including the problem with the energy and power availability for systems like that. And the Department of Energy in the United States intervened to try to mitigate the crazy need for power and energy for these systems and put constraints. Finally, the exascale computers came out, breaking the constraints that were set by the Department of Energy. Anyway, apart from that, I was thinking of the idea of why not combining the computational power available already in the existing computers, especially on the low energy and low power systems like the IoT devices and mobile devices. Prior to that, we developed a high-performance computing cluster out of mobile phones. And in this thesis, we were trying to develop a high-performance parallel computing system out of IoT devices. It might seem similar to the mobile phone, and it is, but its main problem turned out to be the resilience. IoT devices are known to be mobile, moving. It could go to an area out of coverage. It could be connected within other infrastructure and systems that may cause it to fail permanently or temporarily. So it looks like the computing nodes are not stable in this case. So how do we get a high-performance, resilient, high-performance computing system out of IoT devices that are unstable and may drop out of the system at any time? We thought of the idea of using redundancy. So we designed a system where the IoT devices can be divided into groups, and each group share the workload of the rest of the group. So for example, if one group is devices 1, 2, 3, and 4, that means that at any time, devices 2, 3, and 4 can carry on if one drops, or 1, 3, and 4 can carry on if 2 drops, and so on. This is to implement the resilience and to bring the system into completion. Otherwise, we cannot claim that we have an HPC system. Okay, now the real problem was we needed some intelligent solutions, intelligent design to handle the trade-off between resilience and performance. Say that we have in the system, let's assume that we have 1,000 IoT devices. If we want the system to be completely resilient, then we need 1,000 copy of each copy in the system. Actually, they are 999, but let's call them for ease of numbers, 1,000 redundant copies. So if one of them drops, any of the others is able to continue. And in this case, we are sure that we never lose the computation, and we will bring it definitely into completion. The problem is that is the performance. We will need storage for 1,000 copies of each copy, and we will have a problem transferring the data and running the algorithm that will select which one of the 1,000 to carry over when one drops. So this was the main problem of this research. So we proposed a solution, as I said, depending on the redundancy concept, which is known in computer science and computer engineering. But instead of making it fully redundant, like having 1,000, if we want to have a fewer number of copies, what is a good number? What is a safe number to bring the system into completion, but also does not affect the performance, or at least we pay reasonable price in terms of performance? So we need to decide upon the number of duplicates for each node in the system. And we also need to watch the load, the computational load on all the components, and we need to exchange that to be able to select the node that will carry over if one node fails. So which one of the 1,000 is going to take over? So our solution, the proposed solution, was to use duplicate groups. So for example, 1, 3, and 4 is in a group. It's not that simple, but I'm trying to simplify it. So 1, 3, and 4 are in one group, and maybe 5, 6, 7, and 8 in the second group, maybe the other 4 in the third group. So we will see how to decide the number of duplicates in each group and the integration between them. To cut the long story short and provide the main idea of this talk, because of course we passed several stages, we used fuzzy algorithm to divide these duplicates into classes and make these classes set based on the average system load. So we have like light load, very light load, light load. This is just example. You can consider them class A, class B, class C, and so on. This was the main idea, and this was the duplication algorithm and the tuning algorithm for these duplicates, because we can start the system with a number for grouping and duplicates and then modify it as we go. Until now, the only connection is the only connection to the topic of the talk today is that it is a way to implement a high-performance computing system using IoT devices. But actually, it went more than that. To test our solution, we applied this to a parallel pi calculation program. It is a simple program, not that difficult, but we wanted to validate our solution using this program, and this had to be done on several stages. Let me show you the first stage. We wanted to implement this on a small scale. So we got actual IoT devices. They were Galileo boards from Intel, and we built the cluster. As you can see, this is the physical cluster that we build with the switch, and using 512 megabyte RAM, 32-bit, the Intel Quark processor available on these Intel Galileo devices, we were able to run the program and get the results. The problem is, who is going to need an IoT system to build an HPC system out of just 4 IoT devices? This was not the idea. The idea was actually to use the available IoT devices worldwide or region-wide to provide massive computational power. And in this case, we have one of 2 choices: either to get thousands or maybe millions of IoT devices to build up the system, or to go to an existing system where people and the institutions are using the IoT devices and let them stop their work to give us a chance to test our system using them. Of course, you can see that both choices are impossible. So now the solution is system simulation. So we started simulating the system. We simulated already, to start with, we simulated the 4 nodes to test and make sure that everything is running right. This is the simulation program that we developed, and we started running it as if it is only 4. It worked. All the results were compatible with the results we got from the physical system. And this was the result of our evaluation. Now that this worked, the next step was to scale up the system to make it run on large number of IoT devices, which are not available. So we simulated this. So we actually built our own simulator. In many cases, in HPC simulation, you will find simulators already existing, and we will talk also about this. But this does not prevent the need and the ability to build your own simulator when you need it. This was not that difficult. You just build a simulator where you simulate each IoT device by an MPI process. And we have a system. We are now able to generate as if we have 120 processes, as if we have 120 IoT nodes communicating, and we started running the system. Now, why did we need the simulation in this case? Why did we need that for? What the resistance, the resilience is going to do in this case? We are going to drop certain nodes or certain devices. When we did it physically like that, we were physically, manually disconnecting some of these devices during the run, and we see if the other devices are able to carry over and take its work. And then during the run, we reconnected again and we drop or disconnect some other devices. Now in the system simulation, we are able to do that now, but we do it by simulation. So we stop certain processes at certain time according to the algorithm that I just gave a glance for, to decide what is the level of duplication that we are able to use to get 100% resilience. To get 100% resilience, do I have to have 100% duplication or redundancy, as when I talked a few minutes ago? So if I have 1,000 devices, do I have to make 1,000 copies? And the answer turned out to be no. Actually, when we reach the level of redundancy of 30%, we are able to provide 100% guarantee that the system is going to run and complete the result. And these two figures show the number of duplicates. It's just divided not to avoid a very wide scale. This was up to 10 duplicates, and this was up to 60 duplicates. And we can see that we reached the saturation here at less than 30. And we were running at 120 processes. So this was the value of the simulation. There was no way we could have achieved that using physical system, because as I said, we cannot afford, nobody can afford to make a large scale physical system to run this. And it is as if you want to design a new routing algorithm for the internet. Who is going to stop the internet and give us the internet for even a few minutes to run a routing algorithm? It is impossible. So this was the performance evaluation, and these are the numbers. I think we don't need to look at every details in this case, but we started the next step of simulation here using a high performance parallel system, and that high performance parallel system was actually the computer of Bibliotheca Alexandrina. We appreciate, we have several projects running there. This was one of them. And by the way, very recently, this month in June, this project was revived because I have a new group who are going to build on this project. So we revived this project at Bibliotheca Alexandrina. Engineer Yusuf Dakar, actually, we appreciate very much that he re-enabled it, and this was the hardware used. So we started using, instead of simulating on a single computer, we actually simulate on multiple nodes, because we want the processes to be running on different nodes or different cores. In the previous stage, it was simulation running on a single processor. Now we are using multiple processors, and it looks like we were able to validate our idea, our solution. The performance and the results were consistent. We keep doing consistent work. Of course, as the system grows up, the numbers are going to be different, but the consistency seemed to be the same, and we confirmed the ability to provide an HPC parallel computing system on IoT devices to be guaranteed 100% resilient with 30% duplication. These are the results of our testing. We also, as I said, used the fuzzy classes, which introduced a huge improvement. For example, using the fuzzy classes, we were able to reduce the number of duplicates into 14% only, because we capture the uncertainty and provide better performance even than the other systems by 12%. Also, the number of exchanged messages between the processes or between the devices to maintain the integrity of the system were reduced by 61%. So huge performance gain out of this system. I'm happy to provide the papers published to show, to look at the exact results and review them yourselves. Like the case of any simulation, if you want to bring the result of this simulation into the real world, you have to validate it in the real world. And we said that the real world is never going to be able to provide systems of this size. But we can get a larger system instead of the 4 devices. Intel, actually, I was collaborating with them, and they had given me like 12 devices. So we made an IoT parallel computing system with 12 Galileo devices instead of the 4. And we ran the parallel algorithm, and we got identical or matching numbers with what we did before. And the results were very good, actually. And this was the first case study. The conclusion is, as you can see, we can provide a fuzzy mechanism to achieve 100% system resilience with 25% system drop. So if we have 100 devices in the system, we are able to drop up to 25%, which is 25 devices out of the 100, and still get 90% system resilience. And the results, as you can see, with the system drops and 90% system resilience in the extreme case of 70. So you can drop 75%, 3/4 of the system can be dropped off, and we still can get 90% system resilience. I think this is huge. This is very significant. Another example, actually, that was came out recently. A PhD student of mine, now she's a doctor. She's not a student anymore. I'm proud to be a colleague with her now, collaborating on other research. She was working in the area of big data, and the title of her dissertation was Statistical Modeling of Heterogeneous Big Data Sets. So the problem here was big data sets when they are heterogeneous, multidimensional, with high levels of uncertainty. So this is why we used a computationally intelligent approach. The problem with big data, as you all know, big data consists of number of V's. Sometimes they are 3, sometimes they are 40-something. But the most important for us in this research was the veracity, the variety, and the volume. When the volume is big, data classification and clustering seems to be to get more difficult, sometimes impossible, because the data overlap. So it becomes very difficult to deal with well-defined class boundaries. The class boundaries are actually overlapping. And when you try to classify the data, does this belong to class 1 or class 2? Well, maybe both. Sometimes with more membership in class 1 than 2, sometimes the other way around, more membership in class 2 than 1, and sometimes right in the middle. If you exclude one of them, it becomes a big mistake scientifically and engineering-wise to develop a system assuming that this datum belongs to one class and doesn't belong to the other. And this is what the traditional techniques usually do. So we had to deal here with the uncertainty, the heterogeneity, and the required computational overhead to deal with that. When I reached actually this point, I thought, why getting some slides from the other work? Why not continuing from the original slides? But I will be skipping, of course, many things as I did in the previous one. So this, we can start from here. I'll try to quickly, I know I might be about to run out of time, but I'll try to, I promise to try to handle this as fast as I can. So this is what we covered, and this was the main problem. We want to do intelligent. This is different from the hardware design that was in the previous case study. This is now data analytics case study, intelligent data analytics using soft computing and high performance computing. So we want to do mainly data classification, which involves data clustering, and many new approaches do cluster-based classifier ensemble to intelligently do the data classification. As you can see, here is the problem. When the data is massive and integrated, like overlapping, it becomes very difficult to draw a line like this. Even that line is not going to follow a geometric function. It's impossible. You can see that it is not regular in any way. So how to deal with this? This was the motivation. I will skip over many of these things to run into the solution. And here we developed two solutions. This solution is called FCEC, Fuzzified Cluster-Based Ensemble Classifier. So we developed a classifier based on clustering and using soft computing to handle the uncertainty available in the data. This was the algorithm. The paper for this one is already published. And actually, I have good news that the second paper for the next classifier has recently been accepted. They require some minor changes that we are doing this week, and hopefully it is going to be finally published by the next week, and I will be happy to share too. So we used the elbow techniques, and we experimented with several clustering techniques, as you can see, to validate our results. We also used several fuzzy membership functions. Here, as you can see, this is an illustration of the problem. We have data here that for the human eye to see, we had to make this in red and this in black. When we tried to use like circles and triangles, things like this, it was impossible to see it, even with the human eye. So we had to show them like this. The problem is not here and is not here. It is about the data in here. Can we take this and claim that this belongs to the black cluster or the black class and not the red one? Or take these and claim that these are the red but not the black? Of course, there's high level of uncertainty, and this was the motivation for the solution. We developed two fuzzifiers. Not the time to talk about the details of the fuzzy computing used in this case. Mathematics we developed to implement that. I would also, this was the prediction aggregation rule to come up with a decision about the membership of each data point in which class or in which cluster. To start with, we used data sets, downloaded data sets available. As you can see, it is not that representative of a big data until now, but this was important to validate what we're doing. Once we validated, we had to move to the large volumes, a high veracity, high dimensional data. And for that, our only option was to go again for the high performance computing simulation and to go again for Bibliotheca Alexandrina, where we requested HPC access, and we started doing the simulation, coming up with the results, and the results were really magnificent. We published the first paper, and the dissertation passed significantly. She was praised for the work done. Here it's also important to know that to simulate something like this, the difficulty was that there is no physical objects to simulate. We had to turn it into what we call Monte Carlo methods, where we generate data sets according to certain random distributions, and start testing and using high performance computing for simulation. Doing this approach is very important because you can run thousands of experiments. In the case you want to run physical experiments of things like this, you will get 1 or 2 data sets. They will take long time to run the experiments, and you cannot repeat it, because if you repeat it, how would you get another data set of this characteristics? But if you want to generate it using Monte Carlo methods, we were able to do that, and this was these were the results that we came up with. They were published, and this was the second algorithm, because we developed actually 2 algorithms. This algorithm was using HPC to validate the results and using HPC to enhance also the results. So it was double use. We noticed in the first algorithm that regardless of what you do, you always consume computational power and you take time because of the high dimensionality and the high volumes of the data. So we started thinking of the idea, what if we use samples? How can we sample the data to make sample reduction, to reduce the data that we work on, provided that the sampled data remain representative of the original data, and also do the parallel classification in parallel. So this was the idea, and this, by the way, is the paper that was just accepted this week, and hopefully it will be available, published already next week. So this, again, it shows the significance of large-scale simulation. Without that, there was no way to get enough data to validate these things, and even if you get them, it would have taken years to generate these results. These are the metrics, the meters, the metrics that we were evaluating with. It was our approaches was actually outperforming any other previous approach on all the matrices. So this was our conclusion. I had actually 3 more use cases, but I think I don't want to hog on the time and take the time of my esteemed colleagues who are going to talk about me. So we can delay the other examples to maybe future cases. And the relation between this and quantum computing is, as I said before in a previous talk, is that HPC is used actually to simulate quantum computing system, because with quantum computing, the amazing thing is that the software is always ahead of the hardware. It is not like the previous starts. In the previous starts in the other computing systems, it was a hardware that was developed, and now we want to program it to get something out of it. But actually, when the quantum computing emerged, it emerged first as an idea and as a theory, and as algorithms, and all the solutions were developed even before the build-up of the first quantum computing. So until now, we cannot claim that we have a physical, viable quantum computing system able to solve real-life problems, unless within certain limits. But we have much bigger solutions being developed or have been developed. So when these computers are available, we can use them immediately. Actually, some of the solutions are being refined and being studied now, because now we have, for example, what we call post-quantum algorithm, post-quantum encryption algorithm. We reached a point where we are able to see, when we have a quantum computer of certain size, how we are going to decrypt and hack all the encrypted data in the world. So we are now developing algorithms for the post-quantum encryption system, which do not exist until now, but the algorithms and the solutions are actually in progress. So the relation between the examples that I showed here, because this is what I was asked for, to provide examples of large-scale simulations that we conducted already, and connect this with the idea of quantum computing. The main connection is that HPCs, if you do not have access to a quantum computer system now, or if the access you have is not enough, we know that we have so many constraints. Some quantum computers are being sold now, but they are very limited, very small. We know all this, but the thing that makes it up for all this is that HPC simulators for quantum computers exist, and those do not have limits. We can use them and do whatever we want. I hope I cover some case study use cases that give some insight, opens up the idea for the discussions and the idea for future collaboration with all of you students and professors. And I'll be happy in the future to, we said before that we will talk in the future, in a future talk about the main idea of scientific modeling in general, which has to precede the idea of the simulation. So we have many topics to talk about in the future in this regard. And I'm sorry if I took longer time than I should have.
Yes, thanks very much, Dr. Ahmed, for this impressive and nice talk. It's as always very informative. And we are going to have also summer school at the end of August, and this is about scientific modeling and quantum computing. So that will be great to have you. I mean, we still, Engine, Yusuf, and I will still need to work a bit with other colleagues to get everything run. But yeah, that will be the plan. So thanks very much. And we are going to also hear the opinion from Dr. Zidane from the quantum computing side. So for everyone, please put the questions in the chat so you don't forget them, and then we discuss them in the question and answer session. So now we are moving to the next speaker. I'm just sharing my screen.
I stopped sharing, by the way.
Oh, okay. Yeah, thanks, Dr. Okay. And thanks very much for the use cases. Very impressive, and congratulations on the paper. That's also very impressive work. Yes, now it's shared. Yes. So now our next speaker is Dr. Mohammed Zidane. Yeah, so the audience is thanking you for the nice presentation, Dr. Ahmed. So our next speaker is Dr. Mohammed Zidane, and Dr. Mohammed is going to talk about quantum machine learning for large data sets. So Dr. Mohammed Zidane is currently assistant professor in Gardaqa University, and he also has entrepreneurial and scientific mind as well. So he's now serving as assistant professor at AI Department, Faculty of Computer and AI at Gardaqa University in Egypt. He was invited visiting scholar at the University of Arizona in the United States, invited visiting scholar at the University of INTI International University in Malaysia. He's also held 2 granted patents from the United States Patent Office for inventing the main memory of quantum computers, known as QRAM. And also has 10 pending patents from US Patent Office for inventing quantum blockchains, quantum cryptography systems, and quantum database systems. He has published many papers in high-impact journals in the fields of quantum machine learning and quantum computing. He has been awarded many scientific prizes, and he is a reviewer for more than 20 international journals. And also he is a supervisor for and supervised also more than 20 masters and PhD students in Egypt and in the globe. So welcome, Dr. Mohammed Zidane, and we are looking forward to hear your nice presentation and also the impressive work about the quantum memory and quantum machine learning. So, Doctor, we don't hear you.
Thank you.
Oh, yes, we hear you now. Yeah. Welcome, Dr. Mohammed.
Welcome, Dr. Taha. First of all, I'd like to thank Dr. Taha for inviting me to speak in this interesting monthly series. Today, I will talk about how can we leverage quantum artificial intelligence systems for large-scale datasets. Well, we know that any large dataset collected from various sensory sources, including satellites, radio telescopes, IoT systems, self-driving cars, or even integrated information systems, holds a potential value. Indeed, raw data from these datasets is often not useful in its own until a meaningful knowledge is extracted. Extracting this knowledge is a complex and non-trivial process. Indeed, where data is abundant, the challenge lies in transforming it into actionable insights or knowledge. In other words, data is everywhere, but extracting knowledge from it is the bottleneck. Any dataset often hides two types of knowledge: explicit knowledge and hidden knowledge. Hidden knowledge is the most strategic and valuable. In small datasets, skilled human experts can extract both types of knowledge: explicit knowledge and hidden knowledge. On the other hand, in large datasets, skilled human experts can typically extract only explicit knowledge, while hidden knowledge can be extracted using artificial intelligence systems. How do artificial intelligence systems work? Artificial intelligence systems work based on three pillars. The first pillar is dataset of the problem statement at hand that cannot be solved absolutely, mathematically, or according to specific rules. The second pillar is a quantum artificial intelligence. The second pillar is artificial intelligence algorithms. The third pillar is computing resources, which comprises two main items: processing units, which may be CPU, GPU, TPU, or a hybrid system of them, in tandem with the main memory RAM. This raises a question: how do these three things work together? The main memory for classical computers is called random access memory, RAM. RAM is used by classical computers to store a dataset during the execution of artificial intelligence algorithm by a classical processing unit to train this artificial intelligence algorithm from a dataset stored in the RAM. Indeed, increasing the storage capacity of RAM enhances artificial intelligence capabilities dramatically. RAM, which serves as the main memory for classical computers, comprises a set of memory cells. Each memory cell is assigned an address. A classical processing unit communicates RAM through three buses. The first bus is the address bus, the second bus is the data bus, and a control bus. When a classical processing unit needs to write some data to a certain memory cell, it sends its address through the address bus, the data through the data bus, and specifies the operation as write on the control bus. Subsequently, the data is written to the memory cell. On the other hand, when a classical processing unit needs to read a data from a certain memory cell, it sends its address through the address bus and specifies the operation as read in the control bus. Then the data is loaded from the memory cell to the classical processing unit through the data bus. The time complexity to write data to all memory cells in RAM is exponential, and the time complexity to read data from all memory cell in RAM is exponential. This graph, generated by NVIDIA, shows the required resources for development cutting-edge artificial intelligence systems. This graph explains a critical challenge in artificial intelligence development, as large language models are trained on ever-expanding sizes of datasets. The required resources in terms of the computing power and storage capacity of main memory grow exponentially. As large language model performance enhances with more training data, it requires an exponential increase in terms of the computing power and storage capacity of main memory. So without a breakthrough in the computing power and RAM technologies, the progress in advancing cutting-edge artificial intelligence systems remains costly and very slowly. Then, how can we develop efficient AI systems for manipulating large datasets? Quantum computing has the potential to provide us with a quantum processing units that can reduce the computing time from exponential as seen in some problems with classical computers to polynomial time in terms in the input size of a problem. This motivated some researchers to develop quantum machine learning algorithms that operate according to the postulates of quantum mechanics. However, these models and these algorithms are working based only a set of qubits, so they are inefficient for large-scale datasets. Other researchers developed hybrid machine learning systems that operate in a closed loop between a quantum subsystems and a classical computing systems. These models are called variational quantum systems. These models work based on executing simple steps using a quantum subsystems and non-trivial steps using classical computing systems to optimize the parameters of a machine learning that can be used to optimize the learning operation of these systems. However, these systems are inefficient for large-scale datasets, and some of them are swamped in traps. Recently, IBM announced about quantum centering supercomputing system, which operate according by executing some operations on quantum computing systems and other operations in the most advanced supercomputer, which is called Fugogo. And IBM announced that they can achieve quantum advantage by 2026. Indeed, to develop quantum artificial intelligence systems, quantum communication systems, quantum sensing systems, quantum computing system, you name it, the underlying infrastructure should contain a quantum processing units and a main memory tailored for quantum computers. Many firms are striving diligently to develop fault-tolerant quantum computers. This graph explains the recent results of their work. Recently, IBM announced that it has a roadmap for developing fault-tolerant quantum computer by 2029. However, developing an efficient main memory for quantum computer is desperately needed. This motivated us to invent the most efficient quantum main memory tailored for quantum computer. The stylized logo of our invented QRAM is called Q1 RAM. Our QRAM communicates a quantum processing unit through 3 buses. The first bus is a quantum address bus, the second bus is the quantum data bus, and a quantum control qubit. This is the circuit diagram of our invented QRAM, which granted 2 US patents. The first patent was issued in 2021, and the second patent was issued in 2023. The time cost and time complexity for writing data to all memory cells in our invented QRAM is O of 1. And the time complexity for reading data from all memory cells in our invented QRAM is O of 1. And the time complexity for writing data to all memory cells in our invented QRAM is O of 1. And the time complexity to read data from all memory cells in our invented QRAM is O of 1. The main competitive advantage of our invented QRAM is that it is the fastest ever invented quantum main memory tailored for quantum computer. Our QRAM increases the storage capacity of main memory exponentially. It can write to all memory cells at the same time with time complexity O of 1. It can read from all memory cells in time cost of O of 1. And this explains why our logo contains 1 in our logo. Recently, we published a paper in Results in Physics. In this paper, we proved that quantum computing cannot only solve classical problems faster than classical computers, but can solve new type of problems that cannot be solved absolutely using classical computers, even though these problems are quite simple. This implies that we have two types of datasets. The first type is a classical dataset that can be used for classical machine learning to extract knowledge from it, and we can develop some quantum-based artificial intelligence systems to extract knowledge from classical datasets. And there is a new type of quantum datasets that can be extracted, for example, from quantum sensing devices and quantum sensing IoT systems. And this type of datasets cannot be used and cannot be trained and we cannot extract knowledge from it using classical machine learning. So we need only a quantum machine learning and quantum artificial intelligence systems to extract knowledge from it. Then how can we develop quantum artificial intelligence algorithms for large-scale datasets? In fact, because there is no quantum entanglement in classical computing systems, there is no issue in developing artificial intelligence algorithms for large-scale datasets, regardless the detailed structure of computing chip which execute those algorithms. Conversely, to develop end-to-end quantum artificial systems for large-scale datasets, we have to perform two tasks. First, we should establish a quantum chip which should include a quantum processing unit and a quantum main memory, which is QRAM. Then we should precisely understand the detailed structure of this chip. This is because there is a quantum entanglement can be established between the qubits of a quantum processing unit and the qubits of a QRAM. Then they should treat it as a single quantum system. Why this? Because when we go to develop a quantum machine learning system, if we don't take in account the entanglement in quantum machine learning systems that we're going to develop, then we can break and we can violate quantum computing postulates. So we have to precisely understand the detailed structure of this quantum chip, because the quantum entanglement that can be established between the qubits of the quantum processing units and the qubits of QRAM. Then, after we understand precisely this structure, we can go now to develop the steps of our developed quantum artificial intelligence systems for large-scale datasets. And at the end of the day, our quantum AI algorithm must respect the postulates of quantum mechanics, and it should achieve a quantum advantage physically, not mathematically. The take-home message is that QRAM is the fastest ever invented quantum main memory for quantum computers, and to develop quantum artificial intelligence systems, quantum communication systems, quantum sensing systems, quantum computing systems for large-scale datasets and scalable applications, the underlying infrastructure should contain a quantum processing unit in tandem with a main memory for quantum computers. Now I'm going to present a video that shows the main features of our invented QRAM.
In essence, quantum random access memory, or QRAM, serves as the main memory for quantum computers. It plays a pivotal role in efficiently storing and accessing data within quantum computing systems. To grasp the concept of classical RAM, let's consider the analogy of a photo of a cat. When you store this photo on a classical computer, it undergoes conversion into binary code, a series of zeros and ones that represent the data in a format understandable by the computer. Classical RAM then stores this data incrementally, enabling the computer to retrieve and reconstruct the entire image as needed. Classical RAM can store classical data only, but this invented QRAM stores both classical data and quantum data, unlike classical RAM, which breaks down the image into multiple parts and stores them separately. QRAM can store all the data pertaining to the photo of the cat in a single location. This consolidation of data not only saves space, but also enhances storage efficiency exponentially. Furthermore, QRAM offers the remarkable capability to read from and write to all memory cells within its memory simultaneously. To illustrate this concept, let's visualize a set of photos being converted into qubits, simultaneously stored in QRAM. This capability is truly incredible. To implement 16 gigabyte of classical RAM, a total of 137,438 353,472 bits are required. However, in contrast, to achieve the same storage capacity of 16 gigabyte using QRAM, only 43 qubits are needed. Classical RAM's sequential data access from all memory cells makes it slower for large data sets, akin to our turtle's steady plotting pace. Classical RAM operates with a time complexity of O to the power n for data retrieval from all memory cells, indicating that the time required increases exponentially when reading the data from all memory cells. On the other hand, QRAM has the ability to write to or read data from all memory cells simultaneously, giving it a time complexity of O1. This constant cost of access is similar to our rocket's rapid journey, where data can be accessed from all memory cells instantaneously. In other words, you can think of classical RAM as a regular library where you check out books one by one. If you want to gather all the information contained in these books using classical RAM, you'll need to read each book individually in order to find all the desired information within them. It's a sequential process, similar to browsing through each book on the shelf to access the knowledge it holds. With QRAM, you can gather all the information contained in these books simultaneously. QRAM reads all these books at once, providing you with instant access to the information you need. The amazing capabilities of this invented QRAM make quantum computers highly efficient in information processing and will revolutionize dramatically the field of artificial intelligence.
Thank you. I hope I will
Very
be
nice,
finished.
Doctor. Very nice work and impressive work, Dr. Muhammad.
Thank you, Dr. Thank you. Okay, any questions?
Yeah, well, for Dr. Muhammad, because he's gonna leave for another commitment, feel free to drop out the questions quickly for him in the chat. Also for our partners and also colleagues in worldwide in Europe and the States. Also, if you like to carry on the discussion further, please feel free to connect with Dr. Muhammad Zidane. The link of his LinkedIn account and also the emails will be in the shared Google Drive document.
I think this is an interesting question. How many
many qubits in the
how
QRAM?
How many qubits on Q1 RAM? Okay, we invented our QRAM to work on any number of qubits, so it is scalable. Our invented quantum circuit can be implemented on any quantum computer platform and any quantum computer architecture, which may be superconductor, which may be photonic based, which may be natural atoms, which may be trapped ions. So we didn't limit it. We make it open for industry to take our QRAM and manufacture it for any number of qubits. But when we implemented it in the quantum computer that is developed by IBM, we tested 16 gigabyte of data that can be stored in 16 gigabyte classical RAM. Our invented QRAM needs only 86 qubits, and we provide this experimentally. And when we and the results was interesting. While our invented QRAM for 16 gigabyte, it achieved more than 100,000 quantum supremacy compared to 16 gigabyte classical RAM. Yeah, we thank you, Dr. Allen, for this interesting question. Yeah, we invented our QRAM to mark the addresses of the QRAM based on quantum entanglement, and we harness quantum entanglement to write data in QRAM or read data from QRAM. So our invented QRAM mainly is invented based on quantum phenomena, quantum entanglement phenomena. Yeah, and for super, of course, based on superposition and quantum entanglement.
Yeah, so yeah, thanks, Alain. Thanks, Yusra. So Alain is also is now present in the audience. He's also co-founder of and also the president of MolKit-SAS, the startup based in France. And for other also industry partners around the world, feel free if you have more questions to carry on the discussions with Dr. Mohammed. So thanks very much, Dr. Mohammed, for this nice presentation and impressive work. It's really nice to see how the science can meet innovation in the industry indeed. And similar to the HPC work of Dr. Ahmed Shawqi Musa, this also very nice. So thanks, and yeah, look forward to see you in our future. Yep.
Welcome, Dr. Taha. And here, the key message of this presentation is to develop quantum machine learning systems for large-scale data sets. We should use QRAM in our quantum chips. This is the key message.
Yeah. Yeah, thanks, Dr. Mohammed. I think now, yeah, the presentation is clear now. Feel free also to carry on. We will have the school about the scientific modeling, which is now in the pipeline. So might be more information about the QRAM and also the nice work that are running in the stealth mode by Dr. Mohammed Zidan that you are gonna hear about it from him very soon. So good luck in this impressive work, Dr. Mohammed.
Thank you, Dr. Taha. Thank you.
So now we are gonna move on with our next speaker. Feel free if you have more questions to write them in the chat. We are gonna discuss them in the Q&A session. Okay, I'm just checking if Dr. Mohammed is now with us. So Dr. Mohammed, yeah, I think he's now connecting. Okay, so so for the dry out hackathon, so just a couple of announcements as Dr. Mohammed is joining. We are gonna have our dry out hackathon by the end of July. So feel free to join if you'd like to know about hackathons and applying use cases. This will serve as a good preparation for our international hackathon in September in Alexandria, which Dr. Zidan and Dr. Mohammed Shawqi Musa and Dr. Ahmed Shawqi Musa will also serve as a judge and speaker in the hackathon in Alexandria, and also Dr. Zidan will be there as well, and as well as Alain Chancey is also accepted the invite to be in there in Alexandria. We are gonna still discuss also open more opportunities for people to join the mentorship team, but also the jury to act and serve as a jury member in the hackathon. So feel free to volunteer if you like, also to do it in either in person or online as well. So that will be great. We have Yusra also as well, that also is gonna join our hackathon in September. So Dr. Mohammed joined.
Yeah, I'm here.
Okay. Yeah, welcome, Dr. Mohammed.
You're welcome. Thank you.
I'm sharing my screen. So now our next speaker is Dr. Mohammed Amin. Dr. Mohammed is going to talk about advanced applications of machine learning in chemistry and the biosciences. So he's also well known in using the machine learning in a variety of applications in chemistry and also biology. So now a bit of short CV. So Dr. Mohammed has also very nice story. He moved from different disciplines. I was following his story quite close on Facebook as well. Coming from also engineering and until joining multidisciplinary fields from physics, chemistry, and also machine learning. So he got his PhD from City University of New York in physics. Then he did a postdoc in Berkeley National Lab. Then he joined also the Whale City as an assistant professor. Then moved to the Deutsche Elektron Synchrotron, known as DZ, as a research scientist. Then he got a tenure track, and this tenure track position at University of Groningen in the Netherlands. Then he moved to the US Department of Health as a staff scientist. So welcome, Dr. Mohammed, and please, the floor is yours. I'm gonna stop sharing my screen.
Thanks for the introduction. I'll try to share my screen now. So what, I just wasn't sure what's the background of the audience.
So we have mixed audience between AI, also industry, also former Microsoft employees, researchers.
So is everyone aware of knows how machine learning works? I have a quick introduction, or actually a detailed introduction in machine learning, and I thought just to start like this, I wasn't sure about the background, but it might be tedious. If you felt so, you can tell me, then I can jump to the advanced stuff. Okay, so I will now switch to the full mode, and you tell me if you can see the. Can you see the full presentation?
Yes.
Can you see it? Okay.
Yeah, we see the first slide. This covers the world of AI.
Okay. Okay, so I will start by giving an introduction to machine learning, and then I tell you the difference between machine learning and AI, and then I can talk about the drug discovery, machine learning and drug discovery. So maybe first, if we have a case like this, so we have some cells, and these are cells that actual images of cells that taken from a tumor for women, and the idea is that can we use machine learning to classify tumors to malignant and benign in breast cancer. So the idea is that this data set is called Wisconsin data set. Is from the Hospital of Wisconsin, United States, and the idea is that they pull the sample from the tumor with a needle, and then they put it on the computer for image processing, and then the computer can somehow calculate the radii of these circles here. So they do this for both malignant and benign tumors. Okay, and then so they have some patients where they know that the tumor was malignant, and another patients where they know that it was benign, and so they do data analysis on both of them, and then doing this image analysis, image processing, they can get some information about properties of the cell. So if you look here, the distribution of the cell radii, so this is the cell radii, or cell radius, in this case one, for the different cells, benign and malignant, or for the different tumors. And you will see a distribution here for the benign, and another distribution here for malignant. So if you would have a new cell, so let's say that you have a new patient, and you kind of figure out that the cell radius is here. So if you would write a very simple algorithm that checks the radius and then see if it's bigger than 15, then it will be malignant. If it's smaller than 15, it will be the benign. So this is kind of the first step. This is a very short and very simple machine learning algorithm. Okay. So what it does is just check if it's like an if condition. If it's bigger than 15, then it's malignant. Otherwise, it's benign. So, but what's the problem? What is the case if you have a radius here in this region, where you're actually not sure, because this is kind of the intersection between malignant and benign? In this case, so this is what I meant. So here exactly. In this case, you would probably find another property of the cell, maybe not the cell radius, but something else, texture. How smooth is the cell? So there are several properties of the cell that you can use together to decide if it's malignant or benign. So in the breast cancer data set, there are 33, I think 33 or 31 features. And you can combine with your eye. With your eye, you can only do 1 or 2 features, right? But the computer can do hundreds or thousands of features, or maybe millions if you have the computational power together. And I will tell you how, but now this is the idea that the computer can learn more efficient than us. So we are smarter still, but the computer does things that it's hard for us to do simultaneously. Okay, so if you have, these are different features. So you have mean parameters, mean features, mean texture, mean radius, area as well. So the computer could look at all of this simultaneously and then decide if this is the malignant or benign. Okay, so let's give another example, because in the first example we had the case where you have two choices, right? Whether it's malignant or benign. There cannot be something in between. But let's look at continuous variables. So let's give an example from real estate. Housing prices. So if you have a house price if you would discuss if you study the connection between, or the relation or the correlation between the area of the house and the price, you probably see something similar. But let's say that if the area is 50, then the price is 100K. If the area is 100, then it's 200K. So you can guess right away, if it's 200, it will go to be 400, right? Because you kind of learn the trend. So you kind of figure out that the price doubled with the area, and you did it right away, and you can just do the math and get it. So then the question is how the machine learns, how the computer learns this trend. So this is actually, if you look at semi-real data, you will see that it looks something like this. Not exactly 2, and it will not be like an integer factor. It will be something like a float factor. But the price goes up as the area goes up. Okay, something like this. So maybe you have done this many times, not necessarily in Python or in machine learning, but maybe in Excel, you can do the best fit line, right? So I'm not sure if you know this, but the best fit line is a simple machine learning algorithm, because it's kind of learning the trend. The computer learns the trend, and then at some point, if you want to predict a point here, like the data point that you don't have a new data point. So let's say that you decide to sell your house, and then you don't have any house with the same area, but you can just guess here by just going up and getting that data from the line. So the line now is your model. So the line is your model, or your machine learning model. This is an important point because this, although it's a simple regression problem with one dimension, which is the area, it's still considered a machine learning problem. And the area is in this case called feature, and the price called target. This is just a machine learning terminology. Maybe it's pretty easy for you. You already know this, but in case I will try to go faster if this already know it for you. Okay, but the thing is how the computer learns this best fit line. I'm not sure if you heard of this before. The term cost function is the function that we will try to minimize in order to get our machine learning model. So as I mentioned before, so these are the data points, and this is let me go back here. So these are data points. These are measurements that you get maybe from the market, you get from website. But in any machine learning algorithm, we don't touch the data. We don't change them. We might decide to throw some of them out because maybe they are outliers, but in any way we don't change their values. Okay, and what we change is the model, is this line. So we have the data and the model, and the idea is that the model should represent the data as much as we can. So that's why I call the best fit line. It doesn't have to be a line, but we started with this simple example. But how it works? Well, you kind of provide a model, which is in our case the line, and you have the measurements. And the concept is that you have the measurements or the error between the measurements and the model minimum. Okay, and not only for single point, you want to do it for all the points. So if you have point here, point here, point here, you want to make sure that the line passes through them with a minimum error in total, not the minimum error for one or two. Okay, so that's why we have this summation here over the points you have, and yi is your measurements. You don't touch them, you just put them as they are. And this is the straight line equation, right? A plus a node plus ax, a1x. Okay, and it's the minus here is just minus here and minus here. That's why. So the kind of the difference between the measurements and the model should be minimum. This is what we are trying to minimize. I'm not going to go into the detail of this, but we do the minimization with the gradient descent. Math is not that difficult, but it depends on the gradient. So you have to get the gradient for the function, and it's the good thing it's already calculated in many models. So logistic regression, linear regression, everything you will see in different machine learning libraries like PyTorch or TensorFlow or sklearn. It's already implemented. You don't have to worry much about it. But this is just the kind of the math you do, and this is what's called the learning rate. So a new parameter here, maybe this is the intercept of the line equal the old parameter multiplied by the learning rate, which is a very small number, 0.01, and the derivative of the cost function. So this is you do this for all the variables, and you do this for all the models. So it doesn't mean it doesn't make a difference if it's logistic regression or linear regression or support vector machines. You still do it the same way. The only thing changed here is your model. In logistic regression, I will discuss with you now. It's a bit different model, not a linear, not something linear like this, but the cost function concept doesn't change. Okay, so at the end, if we fitted this line, we get this nice equation here. But how do we decide if our line is good? So what people do, and this is maybe you probably heard this before, that the concept of training and testing. So we hide some of the data as we can, as we say that we don't know anything about this part, and train our model on 70% of the data, and then we get a straight line, for example, in the case of the housing problem, and then we use the line to make prediction and then compare the predicted value with the values that we saved on the site, right? This 30%. And then we can evaluate our model. The thing that you probably heard a lot, something like overfitting. So you for this data set, you could have a model like this the model that describes the data set, or like this. Well, you might say, you might, it's maybe obvious that this model has zero error, right? Because the kind of the polynomial here pass through all the points, right? Here you still have some error because there are some distance between the point and the line. So this is low error. This one is low error, but this is higher error. But still, this is not a good model. This is called overfitting. Because if you have a new data point like this one, then when you do prediction, if you continue your polynomial like this, if you have a new data point, the error will be huge. Okay, so this will be the error in this case. While for the line, it will be very, very small. So the idea is not to get the error, the model that best fit your training data set, but it's also the best fit your training data set and also your test set that doesn't really produce a big error. So the overfitting, it means that your model works very well for training, but fails with testing. Okay, so any new data point you will get, it will not be really good. Okay, so in the example we had one variable, which is the distance. Okay, the area of the house, but you could have other factors like the distance, such as distance from center to the city, number of rooms. That's why when we do regression, we do multiple linear regression. So we have many parameters here. So x1, x2, x3, and so on. Okay, in case of malignant and benign, if you try linear regression, maybe you can do something like this. You can say, okay, if this is the radius here, if the radius is higher than x1, then you are here. So this would be malignant. If it's less, then it'll be benign. Okay, but if you added a new point here and then refit your data, you will see that you messed everything up because this point is further away and will shift to the line, so that you will reclassify those as benign, and this is wrong. So that's why for classification problems, we don't do linear regression. We do logistic regression. So instead of having a function that it was a minus a1x, we will replace it with this. So this, if you plot this function, you will get an S-shaped function like this. So this doesn't matter if you add a point here or not, then it will still work fine. So our model then in this case will be an S-shaped function like this. And in 2D, it will look like this. So of course we have more than 2D. We have maybe 100, or in the breast cancer, we have 33D, right? Because we have 33 features. Okay, and if you look from the top, you see something like this, and then this is the decision boundary. So this is the decision boundary here. Okay. It's just machine learning terminology. So another method that is being used is called support vector machine. Is that you instead decide to So you might decide to maybe separate them with different lines, right? So maybe like this. So which one of those you will choose? Okay, so in this case, you would choose the line that maximizes the distance between the points, like here. Okay, so that's why it's called support vector machines, because you kind of add two support vectors here, one in here, one in here, and then it's a bit better than logistic regression, but because it allows you to do some mistakes in between here, and it works fine if you have some outliers. And also it can, with transformation, if you have complicated boundaries like this, where you cannot just put a plane here for decision boundaries between the two types, you can do something called linear trick, where you transfer your data from one dimension to another. So like this, from x to x squared, then you can add your decision boundary like this and separate the two classes. So these are different methods for classification. And there are also the other, so this is based on something called the cost function that you try to minimize. There are other method that based on the information theory, like decision trees and random forest. And then, of course, you have the very famous method, which is the neural network. I'm not going to explain this here, but it's a bit why it's very powerful, why it's very useful, because it kind of catch nonlinear effect. So if you have a dependency in your data set between two features, so that you will not be able to capture the decision boundaries unless you have a model that say x1 multiplied by x2 cube. This will, so the y, which is the target, is dependent on something like this. So this is, you cannot catch with any of the methods we described before, except maybe for random forest or decision trees, you can do something not very bad. But with neural network, with this kind of very complicated deep learning, where it looks like a neuron, you can generate boundary decision that describe this correlation between two features, maybe x1 and x2. And even x2 is not linear, but x1 is linear. So this kind of things can be captured by neural networks. So that's why it's very useful and very powerful. Okay, here in the introduction part is done, and the main difference between AI and machine learning, maybe you heard the two terms before, but for you to know, AI is the more wide used word, and I would say that machine learning is subfield of AI. Okay, so machine learning, you have to make decisions based on data, but AI doesn't have to be based on data. For example, if you design a car that start moving if the traffic light is green, there is no data here. It will just check the color. But if you design something that learns from data, like the example we give on breast cancer, because it needs data to learn from before taking a decision, then it's a machine learning. But AI is a more general word, and machine learning is a subfield of AI when the algorithm needs data to learn from. Okay. Okay. So how many minutes I have?
Yeah, we still have about I think 10 minutes or so you have a bit of time.
Okay, so 5 more minutes maybe, and I'm done. Okay, so how we use machine learning in drug discovery. Okay, so in the early days before computers and AI, we would go to the lab and try all the compounds that we think that it could fit as a drug, and then see within the lab. It takes years, of course, to do many compounds. So it was a very expensive process and very time consuming. So how is it different now? Well, there are several methods to really study drug discovery with machine learning, but I will talk about the AI-based methods. The first method is structure-based. It's not really AI, it's more in molecular simulation. For example, here I'll just give you an introduction about this, but we'll move to the AI part, in which that you kind of get the crystal structure from the internet, from maybe protein data banks. So experimentalists would measure experimental structure of the protein and put it on the web for you. It has the XYZ coordinates of the atoms and the atom types of the protein. And then you can use this with molecular simulation program that calculates the energies of interactions between proteins and molecules and drugs. And you kind of do study on many drugs on the computer. It's called in silico. And then you calculate the energies, and you have some candidate molecules say, okay, based on my calculations, I find that this 10 molecules will be the best in terms of binding energies. Okay, and you run maybe autodock or docking meaning that you are trying to search the protein surface on where the drug can bind. Because in many cases, in our bodies contains, not in many cases, like our bodies contains proteins, right? But in many cases, these proteins are target for drugs, because if there's a function that is messed up because of any disease, then you can try to fix it by just adding some molecule that binds to the protein. I give you an example. In HIV, the virus approach the cell and binds the cell surface, the T cells, and then inject its DNA into the cell and use the cell as a machine to produce the virus again. So each cell can produce millions of viruses. Okay, so one of the drugs that is being approved long ago, I think it was called Cocktail, which is having some molecules that will go and bind to the G protein of the virus, so that it blocks it from binding to the T cell. So it's kind of, if this is the virus and try to find the cell, you put a molecule here so that it doesn't really bind to the cell. Okay, but this is if the structure is known. And this is with the molecular simulations program. But what if the structure is not known? Not all the protein structures known, but now you can also do prediction with AI with AlphaFold. Okay, so with the proteins, if the protein structure is not known, we do some measurements for the activities between the protein and the ligand. So we can measure some activities of the protein when we place ligands in the same in the environment with the protein, and this is kind of telling us how a certain molecule, how strongly it will bind to the protein. So at the end, you want to find the molecule that binds to the protein. So let's say that you tried several molecules and you have for each of them a binding energies. Now you can design a machine learning algorithm that predicts if a new molecule will bind or not. Okay. So how we do this? Like any example, like even the example of the housing, right? So the housing, the house had some features: area, number of rooms, and whatever you add to the model, and then based on these features, you can get the price, right? The same here with the molecules. The molecule has some features, and maybe you can think of them. Maybe think about the molecular weight. You can think about the type of the atoms that constitute the molecule. You can think about the charge, total charge of the molecule. All of these are features, right? And you can use it to predict the binding. Okay, so to do this, we have to work with a simpler form of the molecule, not like the X, Y, Z coordinates of the atoms. That's why people come up with this SMILES representation of the molecule. So SMILES stand for Simplified Molecular Input Line Entry System. So there are a library called RDKit. If you are interested, RDKit. It's a Python library, and it can read the SMILE and convert it to a property. So if, for example, if you pass to it this aspirin, it will tell you how many carbon there, how many double bond you have, the hybridization of the atoms, total charge, partial charge distribution, molecular weight. It can tell you many things. You can use these, it's called molecular descriptors. You can use these descriptors to build your machine learning model. So these are the descriptor, and RDKit is an open source. You may try to use it yourself. If you know Python, it will be easy for you to figure out how to use it. Okay. Also, yeah, so for any molecule, you want to be sure to include the molecular weight as a feature. Log P is, I will not really explain it, but think about it, how the molecule like the water, if it likes to be in water or in oil or in fat. Okay, hydrogen bond donor and acceptor, this is also an important property because it affects the binding between the molecule and the protein. Okay, so this is the idea. You have the SMILES code, you have it's converted to the molecule is converted to descriptors, and then this is a feature vector. So remember, you have to convert all your properties to numbers, because all machine learning libraries only works with number. You cannot do this gradient descent algorithm or minimization of the cost function unless you converted all your features to numbers. Okay, so for binding affinity prediction, there are several algorithms. Mainly the one used is random forest and neural network. Sometimes you use support vector machine for classification if this is an active or inactive. Remember, if you do regression meaning that you are trying to predict the value of the binding energy. You have to use regressor like random forest regressor or linear regression, multiple linear regression. But if you do classification, then you can do support vector machines classification. You are trying to study if this is an active or inactive molecule, not exactly predicting the value of the binding energies. Neural networks work both as a classifier or a regressor, both. So okay, so people not only predicting, I mean, in our field in pharma, you're not really only predicting the binding affinity, but also you predict toxicity, because you don't want to predict even if it can work as a drug by binding to the protein, but what if it's toxic? So it will mess up something else. So then you cannot use it as a drug. So we still use machine learning to decide if the molecule can be a drug or not only by the binding energies, but other things like A here stands for absorption, and I don't remember the other abbreviation for the parameters, but these are parameters that decide if the molecule could be used as a drug or not. Okay, so if you are interested in a case study, you can go to just Google this Tox21. You will see, and maybe write Python example. You will see a really workflow on how to use machine learning to predict the toxicity of the molecules. It's not that we will not do this here. It's not really a drug design workshop, but if you are interested to continue with this, you can do it easily. Okay, so the idea, this is our summary here, that the computer-aided drug design, it's really efficient, not only accelerate the discovery, but also make it much cheaper, because trying all the molecules in the lab is very expensive. So it integrates structural, chemical, and data methods, because you need to know about the structure, you need to know about the chemical property, you need to have to do the data analysis as well. You need the SMILES code to get the description, and machine learning will help you to really come up with a list that you can try in the lab. Remember that we're not saying that the machine learning is replacing the lab, no, but it's just make it more optimized and much more efficient. Okay, so I think I'm done here. If you have any questions, you can ask me.
So thanks a lot, Dr. Mohammed, for this nice and informative presentation, and also the nice work done in these different use cases. So I'm gonna just start the ball rolling of questions. First, you mentioned, of course, translating features to numbers when the training is done on molecules. So what is the best approach, in your opinion, to use in this? I'm not coming from biology, so I don't have an idea about it.
There are several tools already available in Python libraries to do this, that helps you to convert string to numbers. But this is the point. If you have the knowledge of the chemistry and the machine learning, this becomes very useful, because then you know what you need. You know that maybe you want to keep, instead of having C as a carbon, you can put its atomic number. You can place something like the number of carbon atoms in the molecule. This could be a feature. So the most important that you have to make sure that you know what you are doing.
Yeah, right. Yeah, thanks a lot for the answer. So anyone, please drop your question in the chat. Okay, so please feel free to carry on the discussion. I mean, at any time, drop the question, or also you can also contact with Dr. Mohammed directly. Please type, Dr. Tara, your question in the chat.
Okay, thank you for the great lecture. Can you hear me well?
Okay. Yeah, yes. I can hear you.
Okay. First of all, I haven't seen the k-means, how you calculate it for the tumors, and if its directional property can affect. This is issue. I'm thinking you have been talking about supervised learning, so you isolated 30% as a validation set. What about the unsupervised and reinforcement? I haven't heard about it. This is other issue for the drug toxicity and cytotoxics. What about the histocytes and lymphocytes and contradiction with other drugs, or also the smart drug approach?
Okay, for the first question, I didn't talk about unsupervised learning as you stated. So unsupervised learning, you don't have labels, so there's no prediction there. What you do is you do a data analysis. As you said, maybe k-mean clustering, you have a data that you don't know. So let's say that you had samples from patients and you don't know anything about if this is for a certain disease or not. You don't have a label. You don't have something saying benign or malignant. You just have data that you collected and it doesn't have labels. So in this case, you try to find pattern in the data, and then maybe you can label it later. For example, let's think about structures, molecules that have the different oxidation states. So manganese molecules, for example, you can kind of do a data analysis on the bond length, how the ligands, what is the distance between the ligand and the manganese. And you will see then that it falls in 2 or 3 clusters. You will see each cluster has a kind of normal distribution around the center. And later you can relate this to the oxidation state. You can say, okay, the distances, the longer distances is for manganese 2, the shorter distance for manganese 4. So the unsupervised learning usually is used in parallel with supervised learning. And there are several methods, not only k-mean clustering, there are several clustering algorithms. There's also something called principal component analysis, and it's used with dimension reduction. So, for example, you have 1,000 of features, and this is too expensive to run. So you can use principal component analysis just to use the first 10 principal components, and usually you can reach to accuracy of more than 90% of with the first principal component. So I didn't talk about supervised learning, unsupervised learning, because all the time is also wouldn't allow. But also there is something called self-supervised learning, where you kind of have unlabeled data, but you kind of label it yourself and then try to make prediction and see if your model predicts, catch the features or not. Reinforcement learning is something very different, and has more application in something like computer games, where you make a reward for the algorithm when it moves to the right direction. I never worked with reinforcement learning. We are not using it in drug discovery. Okay. The other point, the other questions you asked about the drug, the interactions between drugs and all these things. These also things that you can still predict with machine learning. But this is what I mentioned, that you should be knowing as a scientist. You should know what you are doing. There's no one that can at the end sit and write computer algorithm to tell you that this is the medication you will be using for cancer. No, but in pharma companies, they have different departments, and they work together and then decide if a molecule can be used as a drug or not. So we do more research. We work for the U.S. government. We do more research on certain parts, not the whole thing. So we have collaborators that complement our work, or from the industry they also do. But for us, we don't have the whole picture.
Okay. What about the weight and the bias? Because if the patient is already being fed with another drug, or he has diabetes or high blood pressure and so on, how can you include this in your work?
You can include them as features. Your model it's not something that is not Quran or Bible. You can change it as much as you need. So you can add features, more information about the patients. You can take information that is not useful, and this is what we do. We don't come with a single model and we say we will not change it. No, we change it and we add stuff to really get to the final stage.
Okay. One last remark. When you talk about HIV, there is a CD4, which is still differentiator 4. You didn't talk about it, and you only said that the virus is getting into the T cells to replicate itself. But I'm sure it has also another approach, because it can be hosted in bacteria and take the RNA from the bacteria to replicate itself.
Yeah, I'm not really a biologist, so maybe you know more about this than me.
Okay, thank you.
So, we have also one last question about the data sources. Can you recommend some free data sources or sources for data?
Yeah,
and also with the data from health hospitals.
Hospitals, it's harder, but for the molecule and the binding, you can get the Chamble dataset. Chamble is open source, has data for millions of molecules. You also have binding DB, and then DB data abbreviation for database. It's also a very big data source for drug discovery. I mostly work with drug discovery. I don't work with patient data. So with patient data, it's very sensitive. You have to be careful. It's not easy to get.
And what is the acceptable sample size?
Depends on the method. So if you do neural network, you really have to have a lot of data. Otherwise, you do overfitting, because you have many parameters. It will keep just fitting them, and at the end, it will get you a perfect model. But then if you try a new data, it will fail. So for example, if you have a small data set, let's say 50 points, do multiple linear regression. Don't do neural network. But if you have thousands of data points, 1,000 and above, you can do neural network. In between, do random forest.
Yeah. So thanks very much, Dr. Mohammed, for this informative talk and the nice discussions and answers. We are going to have also future summer schools on scientific computing. This is organized also through Alexandria Library in collaboration with several other entities, and together with other speakers here, we are going to organize this school. So hopefully we just communicate and organize something to fit in this the school about machine learning and the modeling for the drug discovery as well.
Inshallah.
Inshallah. شكرا دكتور محمد. Thank you very much.
تحت أمرك. أستأذنكم أنا يا جماعة.
Yeah, so we are gonna now move to our next speaker. I'm gonna share my screen. So our next speaker is Yusra Farhani. Hopefully I pronounce the last name correctly, Yusra. So you are gonna also say it.
Yeah, it's Farhani with Ha.
Oh, it's Farhani. Okay. Yeah, thanks for the correction. I thought so. I said it with Ha, but yeah, I wanted to make sure there is no he in the word. So Yusra is a distinguished also leader in the quantum computing arena and empowering women students to learn. And she's gonna talk today about advances in quantum software for machine learning and optimization. So a bit about Yusra. Yusra is a quantum computing and optimization researcher at INSA at Lyon Institut National des Sciences in Lyon, and she's also quantum machine learning visiting researcher at Qatar Computing Research Institute. Yeah, sorry for my voice. So she's also founder of Quantum Africa and the former quantum machine learning researcher at QWorld. She's also former Arab Youth Tech Fellow in Artificial Intelligence at Arab Youth Center. That was a part-time job. So Yusra is very active in the quantum computing domain, and recently she has received several prizes, I think, in Emirates and other countries to denote and also highlight her contributions in the quantum computing, also research and educational space, mainly also in Africa and in Algeria as well. So welcome, Yusra. Please feel free to proceed. The floor is yours.
Thank you so much, Taha, for the invitation. Thank you so much, everyone. The talks are really interesting. I've been enjoying my time. I'm not able to open my camera because I'm at the airport right now, so the internet is not the best. Hopefully, it won't cut out during the presentation. So yeah, I will be sharing my screen and let me know if you can see it. Can you see my screen?
Yes.
Okay, perfect. Yeah, so for today's presentation, I'll be talking a little bit about quantum software for applications in quantum computing. Mainly, we'll be focusing on optimization in machine learning. And why is that? Because these two fields are really, really used in as a quantum applications recently, especially with the rapid evolution of the quantum hardware. And we cannot talk about quantum softwares and their evolution without talking about the evolution of quantum hardware. As Dr. Ahmed mentioned before, currently, like companies and research labs are competing to provide a hardware which can help us to have or to produce different simulations and different applications for quantum algorithms. This hardware varies different types. We have real quantum hardware and we have quantum simulated hardware. This quantum simulated hardware is simulated on HPCs, on CPUs, and on GPUs, and it's used to run these quantum algorithms that we as people in the quantum software part are actively developing. So I've been choosing like only 3 examples for this presentation, and there are many few others. Starting first by the IBM Quantum. So as most of you in the quantum community heard, so IBM have the roadmap of achieving a fault-tolerant computer by 2029, but they have been announcing their Heron chip in 2023, I think late 2023, with 156 qubits. This chip has 3 times lower gate error than all the previous devices that IBM has been working on, which make it more scalable. The second example, which is the Willow, developed by Google Quantum AI. What makes it a breakthrough is the alpha qubit, which is a classical framework that has been used to reduce and control the error on the superconducting chip. And this made the Willow chip as the first superconducting chip that has reached the below threshold error correction. Another example, which is a very famous example, the D-Wave quantum annealer. So as known about D-Wave, they have a very huge machine with more than 500 couplet qubits. And D-Wave has been known by tackling several applications in industries, with governmental projects, as well as with labs. And their recent announcement, if I'm not wrong, it was like in February 25, they have claimed that they achieved quantum advantage over one of the best supercomputers on material simulations. These are only few examples that led to a huge growth in quantum algorithms. Of course, there are many other hardware which has been announced lately, especially in 2025, as it is like the year of quantum science and technology by Microsoft and Amazon, etc. But this has pushed us as quantum scientists, especially in the field of algorithms and models, to like push to the limits and to try new algorithms, new approaches, tackling different use cases, either in molecular simulations, in biology, in chemistry, in optimization, especially in like tackling NP-hard optimization problems. So a lot of leading institutions, including ETH Zurich, Xanadu, and Quantinuum, and D-Wave. I mentioned these because their main focus is on quantum machine learning and quantum optimization. Well, there were like a lot of publications, like on arXiv only between 2024 and 2025. There was more than 6,000 papers have been published on quantum machine learning itself, and more than 100 1,400 preprints published on different quantum optimization models and algorithms, including the quantum approximate algorithm or the variational quantum eigensolvers, different variants, and also the QUBOs, the quadratic and constrained binary optimization models for different use cases. Now, before moving to introduce the different softwares, so I selected like a bunch of softwares that I'm usually using during my current research, either in machine learning or optimization. But I wanted first to introduce for you what is quantum machine learning. As you know, it's the hype because AI is the current hype in computer science. And in quantum computing, with the emergence of AI, now quantum AI has been introduced as the new hype in the field. So quantum machine learning is usually referred to as a field that it is on the intersection of quantum computing and classical machine learning. It explores how quantum computers can be used to improve or accelerate machine learning tasks, and at the same time, how machine learning can be used to better control and optimize quantum systems. There are different definitions in the literature for quantum machine learning, but the most appropriate definition that I like the most is that quantum machine learning, or as we refer to as QML, is the study of algorithms that run on quantum computers and are designed to learn patterns from data, leveraging quantum phenomena like superposition, entanglement, and interference to gain computational advantage. And why, more specifically, the last part, to gain computational advantage? Because what is spread now about quantum machine learning, is the fact that most of people are trying different variants of taking like a classical machine learning pipeline and trying to inject quantum within this pipeline, which is not wrong, but not the best way to do quantum machine learning, as most of the scientists, they wanted to explore this area from a real quantum perspective, or a real quantum eye, where we can see how can we solve the different problems that we face in the current classical machine learning using quantum phenomena. So why quantum machine learning? We're basically facing several challenges in the classical machine learning. Between brackets, this is like under constraints, because as we know that the quantum hardware is not 100% developed. We still have noisy computers in the NISQ era. We still have computers with very limited number of qubits, and that's why we are not able to process large data sets. But we still have really powerful algorithms and quantum models that can simulate or can be simulated on quantum-inspired computers, and that shows also an advantage over classical algorithms, either in medical imaging or an optimization. So for the challenges that we face in the classical machine learning, so first of all, as Dr. Mohammed has mentioned before, we deal with large feature spaces. So we do have a lot of features in our data sets. And dealing with these features, we do need a lot of computational resources and computational powers. And that's why we do have the quantum advantage in parallel, where we have the superposition that will allow us to explore a lot of spaces, a lot of feature spaces at once. And that's what will lead us to consume less computational resources. The second thing is the high dimensional data. So we often in classical machine learning try to do high dimensionality reduction using, for example, principal component analysis, PCAs, and other methods or algorithms. In the quantum field, we try to reduce dimensionality of our data by mapping it into Hilbert spaces and calculating our embeddings and representing the data in a different way than the classical data. We do also have slow and very slow kernel methods or kernel evaluation methods in the classical machine learning. And that's why scientists, they created a new algorithm called the quantum kernel method, which is faster and more secure. Why secure? Because if you try to see like the different implementations for the quantum kernel, it's usually implemented as a graph structure where the different nodes or different kernels, they don't really interchange the data, but they only interchange the features, which makes our full data set so secure, and the interchange between the different kernels is so secure. And coming to optimizing the loss function of our quantum or classical models, optimizing often takes a lot of time. It's an iterative process, which we have replaced in quantum machine learning models with different quantum optimizers, either by formulating our loss function as a cuboform, solving it with quantum annealing, or using ansatz and VQEs in order to optimize over the loss function. There are several types of quantum machine learning algorithms. Well, I try to classify them into 3 categories. Some they classify them into 5 categories, some into 2 categories. So the first category is quantum enhanced machine learning, where we use quantum systems to improve machine learning. We have different variants of the current classical machine learning algorithms employed or designed for quantum hardware. For example, we have quantum support vector machines, QSVMs, we have quantum neural networks, quantum k-means, quantum classifiers, and quantum GANs, and several architectures that exist in the literature and that have been proven an advantage over classical algorithms, but only on like samples of data sets. There is the second type, which is classical machine learning for quantum tasks. As I mentioned before, with the willow shape of Google, basically the Google DeepMind team, they have been collaborating with the Google Quantum AI to develop the alpha qubit, which is a classical machine learning model employed to for noise mitigation on quantum chips. There are also like several quantum classical machine learning algorithms that are used to optimize quantum circuits, their depth and the number of qubits used for these circuits, and to optimize also the parameters or the control parameters for quantum circuits. The last type is the hybrid models, which is the type that I don't really prefer to work on. The hybrid models are a mix between classical and quantum models, where, for example, we take a normal neural network and we try to add some quantum layers within this neural network in order to experiment the output and how would, for example, a classification or prediction tasks perform if we have a hybrid architecture of quantum and classical layers. Another example is for example, to use the quantum Hadamard edge detection as an edge detection algorithm and then feed the results to a normal CNN. Another example is to have or to extract the feature using a quantum feature map and then use a classical optimizer at the end of the model to be able to perform the tasks that you have. This is for the quantum machine learning. I just wanted to give this brief introduction before diving into introducing the different tools that exist in the literature. Now about quantum optimization. So quantum optimization is my current field of research, where we try to use different quantum phenomena, especially tunneling and superposition, in order to improve the solutions of complex optimization problems, usually NP-hard optimization problems or NP-complete optimization problems, mainly in scheduling, in protein folding, in portfolio optimization, and applied on different like problems such as flow shop scheduling, job shop scheduling, max-stat problems, etc. Like there are several like optimization problems that has been tackled using quantum optimization, and this started like since 2014 actually, which is not really new. It has started even before we have a real quantum hardware on the table. So what is interesting about quantum optimization is that We deal with the optimization problem as the Hilbert space, where we try to initialize the Hamiltonian. We try to optimize over this Hilbert space using quantum tunneling, which allow us to escape the local minima until we get the best or the most optimal solution that corresponds to the lowest energy in that space. And one of the application, or one of the the applications for quantum optimization is trying to probably modelize the quantum optimization algorithm as a QBO model, quadratic and constrained binary optimization, where we take it from a classical objective function and constraints and decision variables to a quadratic and constrained binary form that quantum solvers are able to solve. Not only quantum annealers, but even quantum-inspired solvers. This is one way to do quantum optimization, and there is also several gate-based algorithms, including the quantum approximate optimization algorithm and the variational quantum eigensolvers, which are gate-based, usually implemented on Qiskit. These are like some of the examples for quantum optimization algorithms used in different applications. Now moving to the quantum software or the frameworks for quantum machine learning. There exist several frameworks in the literature, but these are the most used ones with high applicability on different fields and a lot of resources. If you are interested in using them in your current research, they are open source, they are available and accessible in different regions, and their documentation is very, very strong. So you won't be alone when you use these tools. The first and the famous one is the Penny Lane framework. Penny Lane has been created by Xanadu, which is a Canadian company, and their main focus and main work is quantum machine learning and quantum optimization. So it's a hybrid quantum classical machine learning framework that allow us to create gate-based quantum circuits, create different quantum models, including quantum classifiers, GANs, quantum CNNs, and quantum kernels as well. So it supports PyTorch, it supports TensorFlow and JAX. And what is interesting about Penny Lane is that the backend is connected to different other hardware providers, including IBM and AWS brackets and Strawberry Fields. They have the differentiable quantum nodes, which we're gonna use within like your algorithms when you use Penny Lanes. And what is interesting about Penny Lane is that you have a lot of challenges on their platform. You have a lot of applications. You have a lot of ready work and ready code that you can read, you can understand, and you can re-implement in order to understand how can you develop a quantum machine learning model, a quantum machine learning circuit for different applications. The second and the most famous SDK is the Qiskit, provided by IBM Quantum. So Qiskit have a whole module for quantum machine learning applications where you can directly import different libraries and use them with their fully developed functions. You do have the estimator QNN, you have the sampler QNN, you have the neural network classifier, among others. You have also the ability to connect to IBM quantum real devices or the IBM Q runtime and run your code with like small data sets and have experiments. You can create a same as Penny Lane, you create quantum kernels, quantum CNNs, quantum GANs, etc. And it's also rich. So the documentation available on Qiskit is very rich with a lot of examples that will help you to navigate your way if you want to learn more about quantum machine learning and its applications. Another example is the Lambic, which I have been using when I've worked on quantum NLP. So the Lambic is a framework created by Cambridge Quantum and Quantinuum. Lambic deals with NLP with the different completely different approach than the classical NLP, where you need to deal with vectors of embeddings and consume a lot of computational resources. So Penny work based on the category theory, where we transform our input data, which is text data, into string diagrams, and from string diagrams we create trees, and then from trees we create quantum circuits that can be run on different quantum hardware, including the IBM Qiskit and the Penny device, which is a classical hybrid device. So for Lembic, it has been also used, but not widely used, because for now it supports only English and Japanese, and there are several works to make it more scalable and support several other languages, because as it operates on the CCG grammar, it's kind of hard to try to map a whole language into CCG grammar and then like make the grammar model or the parser understand these CCGs and build upon it like quantum circuits that can really represent the different interactions and relations between words and sentences. But still, you can also find a lot of resources about Lembic and a lot of applications and also several papers on arXiv about their work. We also have TensorFlow Quantum, which is provided by Google and built on Cirq. So TensorFlow Quantum is used also to create quantum encoders, classifiers, quantum CNNs, and also used for quantum reinforcement learning. The thing is, it's limited to the Google's hardware, and lately I think they stopped supporting the Cirq. So I stopped working on Cirq since 2023, so I'm not sure if they still added new functions to TensorFlow Quantum or not, but it's also efficient when it comes to more specifically creating quantum autoencoders and decoders. And we have also GenQ AI by Quantinum. We still cannot access the GenQ AI yet, so I still didn't experiment with it, but according to what I've been reading about it, it's a fully quantum enhanced generative AI, a framework fully built for large scale data sets and scalable also for like the NISQ computers and also the fault tolerant systems. So for the applications of the GenQ AI, they vary from physics to material science and life science. One of the applications of the GenQ AI is for chemistry and molecular representations. These are like some of the few frameworks that exist for quantum machine learning, and there are other frameworks which are built on these or the previously presented frameworks, especially Penny. So a lot of quantum machine learning frameworks that appeared after all was built on Penny and was like created for specific tasks in machine learning. The second type of softwares is mainly software dedicated for quantum optimization, and this software mainly help users with no prior background in QUBO modeling to formulate their NP-hard optimization problems or the optimization problems that they are trying to solve into a QUBO model. So often the translation of normal hard like constraints and objective function to QUBO requires a lot of time and a lot of expertise in both quantum computing and operational research, mainly mathematics. So you need to well create your model in order to make sure that the solution you get are feasible and your model is well interpreted by the quantum hardware or the quantum simulated hardware. So one of the newly created framework, this framework has appeared in 2000, the first version in 2023 and the second version and the enhanced version in 2024 is the AutoCubo framework. So the AutoCubo works as follows. It translates a high-level description of your optimization problem as like a normal Python code of constraints and objective function into a Cubo matrix. And it handles the penalty terms, it handles the sampling, and it sometimes handles which hardware you should use to be able to run your Cubo. This tool is very effective. I've been using it in my current research, and it shows like a very impressive results, because it took us like more than 1.5 years to be able to develop like our Cubo models, and then within like few minutes we were able to have our Cubo using AutoCubo framework, which is very good for people with no prior knowledge in Cubo formulation. The second tool is the D-Wave Ocean SDK. So D-Wave, they have an SDK called Ocean, and it has several modules within it. So we have, for example, the D-Wave Cubo Solve, which allow us also to solve Cubos using the D-Wave, either like the hybrid sampler or the quantum sampler or the NL solver of the current D-Wave. We do have also the BQMs and the CQMs, so the binary quadratic models and the constraint quadratic models. So these two models, they allow us to convert our optimization problems into a model where we can adjust on their parameters, like the timeouts and the penalty, in order to be able to solve our optimization problem. And D-Wave is known to be very efficient. So they have beaten in their recent research the current classical hardware for certain optimization tasks, especially on the tired instances. So tired instances are like famous instances that we refer to in the optimization community. So these are like the best results for certain optimization problems that exist, and quantum computers are trying to beat these best results. In Qiskit as well, we do have Qiskit optimization. So we can create gate-based variational circuits for optimization problems, including the QEs and QAUA. And the problem or the pipeline is somehow similar. So you need, first of all, to map your problem into Cubo and then to create your quantum optimization model. So you are able, of course, to run it on IBM quantum hardware or one of the IBM simulators. And we do have also Penylane. So Penylane, they have QML QAUA, which is used for quantum optimization to minimize, mainly used to minimize cost functions in quantum machine learning models, but also to solve Cubo problems. They have a whole workflow for quantum optimization. They have customizable ansatz, and then you can also run your backend on different quantum simulators and quantum hardware, including the IBM and AWS brackets or Amazon brackets. We have CuboGL, which is a Julia-based framework. So this is an old framework. Not very old, actually. It has been published, I think, 2000. The first version is in 2020, if not wrong. So it's the main idea of AutoCubo, where we wanted to make it easier for people to generate their Cubo models and run them on different quantum simulators or quantum annealers. So CuboGL is based on the Julia language, and it provides a full pipeline of converting a high-level description of optimization problem into a Cubo form that you can run it on several hardwares. It also supports Eisen models, Cubos, and formulation of Hamiltonians if you want like an abstraction for your optimization pipeline. There is KubeVert. So KubeVert is a PhD project, which is really interesting. A PhD project of one of the students at the University of Maryland. KubeVert can also allow you to create QBOs on PCBOs, and Eisen problem formulations, and it handles mapping the constraints into the objective function. It handles the penalty terms as well, and it can allow us to have like Cubo matrix within a short amount of time. You just need to understand the problem or the optimization problem that you're dealing with, and then formulate it in a way that you can generate the Cubo or the Cubo using the pre-built functions of KubeVert. This is not the only tool that exists for transforming like quantum optimization problems into QBOs. There are other tools. There is like the Munich Quantum Toolkit or Quantum Auto Optimizer, as they name it, which is published in 2024. And this also provides a whole pipeline for quantum optimization. So you can start from selecting your optimization problem, and then you can convert it into a QBO form, and then they provide you with several methods to calculate the penalty for your QBO model. Penalty is so important for your node because with the QBO you need to add your constraints into the objective function so that the model become unconstrained, and then you need to give these constraints a certain way so that the solutions you get are feasible. And then how you control the weights is via the penalty term. So the penalty term is often calculated manually, but it can also be calculated using one of the algorithms that these optimization tools are provided. For example, one famous algorithm is the Verma-Lewis, which is the sum, which calculates the sum over the coefficients and presented in the penalty term. Yeah. So these tools are really efficient, and they allow us to make quantum optimization more familiar for people who are really not experts in the field, but at the same time, it allows us to have different experiments. So instead of me wasting a lot of time to manually formulate my QBO, I can have several versions of QBOs formulated within a few minutes or seconds, and then test them on several hardware and compare them, etc. Yeah, so because I wanted to keep the presentation short, and I also want to receive some questions, but I wanted to talk a little bit about the limitations. As I said before, the software is developing. There are many other softwares that I didn't mention in this presentation, and that like few research labs and groups are working on them. We're still facing hardware limitations when it comes to noise and the coherence of the current quantum hardware, the limited qubit count, and the connectivity when it comes especially to quantum annealers or quantum optimization specialized hardware, as well as the limited access to these hardware. So it took me like several months in order to complete like a small data set using the available quantum optimization hardware that exists, because you only have like 20 minutes per month. You need to really or carefully design your algorithm in order to be able to access this hardware and to run your algorithms efficiently. Otherwise, if you need to pay, and then it's sometimes really expensive for some institutions, and sometimes the access for certain quantum solvers is not even available in certain regions, including, for example, D-Wave in Africa. Yeah, so this is one of the limitations that me and many other researchers are usually facing when it comes to doing real work in quantum optimization or quantum machine learning. But yeah, we're still optimistic. We're still building our algorithms. There is a lot of research going on in our labs, and we are aiming for like better use of our algorithms whenever like a more developed hardware is available out there for our use. So yeah, thank you so much, and feel free to ask questions if you have.
Yeah, thanks very much, Yusra, for this nice and informative talk. It's a really nice overview about these and available software development kits and also the quantum software ecosystem around it. So there are several questions in the chat. We are gonna discuss them in the Q&A session. So we take all questions at once. Now thanks again for this nice presentation and also the impressive work you are doing. And now we are going to move to our next speaker. Please feel free to write your question in the chat. So we are going to discuss them before you forget. So we discuss them with our esteemed speakers. Now we are going to move to Ahmed Salim. And Ahmed is now gonna give us very nice talk about also the quantum ecosystem. We have heard so far the story starting from Dr. Ahmed Shawqi Musa about the HPC larger scale simulations and how they are useful for even testing and validating very complicated use cases, especially related to IoT. But now, as he mentioned, for the quantum computing, and we have seen the QRAM was Dr. Mohammed Zidan, and from Mohammed Zidan, we have moved to Dr. Mohammed Amin, and with Amin, we have seen how the machine learning is used and needed for drug discovery, and with Yusra, we have seen all of the available software and quantum machine learning. Now we are ending up with a story with Ahmed about, okay, now we have all of these settings, what kind of resources we have available and the ecosystem around it. Feel free to write your question in the chat. I'm going to share my screen now to introduce Ahmed. Hopefully now it is visible. Yes. Okay. So Ahmed is going to talk about overview of the quantum software ecosystem in Saudi Arabia and also at IBM. So Ahmed is a seasoned IT professional with 22 of industry experience, currently excelling as a technical leader at IBM. He's a senior technical leader at IBM. He's also effectively guided over 40 clients across diverse sectors, including banking, insurances, retail, oil and gas, and the government agencies in their transformation journey. He also has holds several certifications, and as Open Group Master Certified, he's also serving as a public speaker at IBM Academy of Technology, business partners, and regional events like IDC, LEAP, InvestTech, and many more, where he's also represented IBM hybrid cloud and digital transformation, AI, and the quantum computing strategies. He also has a passion in exploring and leveraging trending technologies such as generative AI, smart processes, cloud technologies, blockchain, and quantum computing. Welcome, Ahmed, and we are looking forward to hear your presentation. So the floor is yours.
Assalamu alaikum. Thank you, Dr. Taha. And thank you all for the time and the attendees. I think it's a very long session. I know. I'll try to make it light and quick. I think I have 30 minutes, right?
Yeah.
Okay, so let me share my screen. Oh, I think I have to reconnect because the sharing, you know, Mac. Okay. So I'll reconnect again, please, because of the Mac is recording.
Okay, so yeah, Engineer Ahmed is gonna join us shortly. He's just making rejoining the session. So there is several also question in the chat by Alain. So we are going to discuss also them in the Q&A.
Sorry for that. I'm trying to now share my screen. It should share the full screen, right? It shouldn't be this one.
Yes. So now we are seeing your web browser only, LinkedIn.
Yeah, I'll the whole screen. Okay, so can you see my screen now?
Yes, we see your screen, but we see now the Google Meet. Yes, now we see your presentation.
Okay, that's cool. So okay, so as I promised, I'll make it light and quick. It's about IBM. I am Ahmed Salim. I'm technical leader and quantum ambassador in IBM. There is an important disclaimer that this is a personal invitation. So the information presented in this session, it's my own work and it doesn't necessarily reflect the opinions of my employer. Okay. It's all the public information. I gather it for you just to give you an overview about IBM, what is doing in the market when it comes into the quantum computing and the ecosystem when it comes into the Gulf area. So when it comes into IBM has like two main goals: to bring the useful quantum computing to the world and make the world quantum safe. As we can see from all the presentations for the doctors and professors for these presentations, they prove that we are trying to build a quantum computing that's useful to the world. We have many use cases, many applications, a lot of research work is being done in this area because it has a potential, it has a value, it has even a large market in the world where we can get a lot of benefits out of it. And the second part is the world, to make the world quantum safe, as Dr. Ahmed referred to the quantum cryptography or quantum safe. I didn't include this part in my presentation. I'll just give you an overview or high level talks about the quantum safe. Quantum safe started with NIST, National Institute of Standard and Technology in the United States, where they released a contest back to 2016 to find a new encryption algorithms to replace the classical one. Now we are talking about the computers as a classical or traditional computers, as long as we have a new way of computational stuff, which is the quantum computing. So they are invited all the giants, all the tech giants to come up with a new algorithms to be quantum safe, unbreakable by classical computers or the quantum computers. And this contest, they shortlisted 4 quantum algorithms, 4 quantum encryption algorithms, 3 of them presented by IBM, invented by IBM. And it's now like one of the best practice that we can start replacing the classical encryption or the current encryption that we are using the quantum safe or cryptography algorithms. So out of this, what we can get some overview of the importance of the quantum. And this is the first, in my opinion, the first tangible implementation of quantum. Definitely quantum safe doesn't require any quantum machine to be implemented. It's just an algorithm that you can use it in your enterprise. NIST is they mandated all the federal agencies by 2035, I think, or near that, more or less, to be quantum safe. So all the federal agencies in IBM are mandated to change their encryption ecosystem to the quantum cryptography algorithms. Okay, so this is the most important, in my view, use case that we can get benefits out of the quantum computer. And the biggest part is the having a useful quantum to the world, and this will be developed by scaling beyond the classical computation that we are using as of now. And definitely IBM or Google or any hyperscaler or any technical provider will not be able to work it by itself. It should be through the joint efforts between the academic institutions, the communities, and the ecosystem around it. Because this is not only a solid, still not a solid technology. It requires everybody to interfere, to help, to develop such a technology to the world. So the quantum machines must be performant, because this is the main objectives of having a new technology like the quantum, because we have the classical computers, they have some problems and unable to resolve it using the classical computers, even by the supercomputers that we have as of now. But now in the quantum, we need it more performant and even easy to use. We know that the quantum in the early stages for non-experts in this domain or maybe non-researchers, it might be a little bit complicated as we speak, because still we are building this system ground up. As you can see from all these brilliant sessions, it's all about the low-level architecture of how we are building algorithms, the quantum, how it works, and all this stuff. For normal user, if you can say, when it comes into dealing with the normal customers that you want to explain quantum, it's hard to digest all this information, right? A lot of scientific stuff, but he needs something that easy to use. It's maybe this is back days for the first days of having computers, right? So I think this is the area where we need to focus. We need to simplify it to different users, so business users will be able to use it in a proper way without any complications. So IBM is focusing on many steps on this journey. We need to build scalable quantum computers, and how we are doing this in IBM, we are developing a roadmap, a very ambitious roadmap. All the doctors in the previous presentation, they mentioned about the quantum utility, quantum advantage, and the announcements of IBM. So this is IBM, what they are focusing. They are focusing in the roadmap in two main areas. The first area is developing a production systems, starting from the hardware up to the software implementation algorithms. And the other one is the innovation and the research. So these are the two parallel tracks that IBM is working on. Beside that, we are not working alone, and we are pretty sure that IBM alone will not break through in this technology, but we need a community, academic, as I mentioned, researchers, business partners, startups, scientists, and all these come together to collaborate and build the quantum community all over the world. And by this only, we'll be able to progress and discover more solutions for the problem that we cannot resolve by the classical computers. At the end, we have Qiskit, like Dr. Yusra highlighted in the last presentation. This is the toolkit where the developer can use a Python friendly SDK to be able to program, build circuits and algorithms to be executed on IBM the quantum machines. And it has been, as you know, Qiskit has been adapted by many other quantum vendors like Amazon and Google. So you can run Qiskit on a different quantum vendors. And this is a very brilliant move, because IBM, when it comes into, okay, we build a new machine, quantum machine, how we can let the programmers or the developers build their own solutions. We don't need to come up with something new. People start learning from scratch. We decided, or IBM decided, to use Python, as this is the base programming or development programming languages to build your quantum algorithms. And we avail the Qiskit, the SDK, to be able to download it and build your own algorithms. We have many versions of Qiskit. We keep enhancing on it. and this will come up on the coming slides when it comes into the roadmap. Okay. Definitely the quantum safe, along with all this effort with IBM and the partners and communities, we come up with the quantum safe algorithms shortlisted by NIST, and definitely NIST is a reference for all the security government organizations worldwide. As we can see here, and all know, we have some hard problems, non-deterministic. We have quantum easy problems, and we have classically easy problems. With classical easy problems, we can solve it by the traditional machines. And the hard problems we're unable to address using the classical machines that we have, that we use currently. And we have some quantum easy problem, but how and when can we resolve the hard problems that we are unable to resolve using the traditional or classical machines? Actually, it has been already started. If we can look into this graph, we can see the investment, the number of active POCs in the industries over the years. And we can see that the most, by 2024, we have the most use cases of POCs is being done on the healthcare, and followed by the materials, right? So these are the main two hot topics. And as you can see, Dr. Muhammad Amin, he explained the machine learning and how we are using it, and Dr. Yusra referred to the quantum machine learning as well, and they will be like better together when it comes into having a tangible outcomes with the hybrid approach, right? So the momentum is very big. We have 55 billion of global investment worldwide. Name it, people, some countries, they develop their own quantum entities to do the research and start doing some research about very critical use cases when it comes into the energy, materials, finance, aerospace, high tech even. Okay, so the potential is very high. The investment even is very aggressive when it comes into the quantum, because everybody knows what is coming in the future. And when it comes into the IBM roadmap, as you can see, we started from 2016, and we have a roadmap for 2033 and beyond. Okay, and as you can see, IBM is working in multiple layers. We are working on the hardware layers. We are developing our own quantum processors, couplers. We are working on kernels, algorithms. So we are handling the full stack from bottom up. And as Dr. Ahmed mentioned, Dr. Yusra and Dr. Muhammad, by 2029, IBM is expecting to achieve the quantum advantage. From time to time, we hear about X company, we reached the quantum advantage. Y company, they reached the quantum advantage. In my personal opinion, still all in the research, they might achieve the quantum advantage, but there is a lot of constraints out of it. It may be in a lab, but when it comes into the real use cases, I don't think so it will fit into the quantum advantage. And in the coming slide, we will differentiate between what is the quantum utility and the quantum advantage. But this roadmap, you will find it in details on IBM website, and breakthrough of all these achievements till the moment. As you can see here, 2025, this is the year that we have. And by the way, if you look into the roadmap starting from 2016 till 2024, IBM never miss a milestone. They are always meeting these milestone, achieve it. And the 2025, definitely this will be a very interesting year, because by 2026, this is what IBM is promising about the quantum. Okay, by 2029, as IBM can see, it will be too late for anyone who doesn't invest, like from customers maybe, or start exploring the quantum use cases, because the many organizations now start in investment on the quantum. Banks worldwide, financial institutions, even private healthcare entities. So these people, they will outperform when it comes into the reaching the quantum advantage. And in two ways. First thing, you are doing now the research, you are realizing the potential that is waiting for you when it comes into the quantum research and the quantum use cases that you can use inside your industry. And second one, in the quantum security or quantum safe, okay? So by 2022, why we are worried about the quantum advantage? Because we can see that the concept of harvest now, decrypt later of the internet security or the internet encryption, someone is sitting somewhere in the world, is harvesting the internet traffic. And once we reach the quantum advantage, these all encrypted traffic we will be able to decrypt it by the quantum machine. This is the promise, right? So it's a very critical year, 2029, from IBM perspective, that we need to be ready from now. Whoever will be behind, definitely he will not be able to cope with these changes. So I will not repeat what I just mentioned about the roadmap. I want to focus on these powerful years, or really very critical years when it comes into the evolution of developing new quantum chips. As Dr. Yusra highlighted, we have now the latest and the powerful Heron chip, where it will enable us to work on a modular base. And this is the base for IBM System 2, where we can have multiple quantum systems working at the same time. Till the last year, we have only one quantum machine can run using one processor. So now we can have a modular way. And we are keep evolving to be able to build a quantum system where we can achieve the logical qubits, not the physical qubit, which is something nobody knows till now, how many physical qubits can be translated into a logical qubit, but this is still area under research. And I'm pretty sure that maybe by 2026, we will be able to have a logical qubits definition, if it's not before that. So what we are living now is the quantum system in the second quantum revolution in history. Because if you look around, currently we are using the quantum in many areas like the laser, the MRI, atomic clocks, transistors, and all this stuff. They are using definitely the quantum, and this is the first evolution. But the second one, we can see that the first wave, it generates like tens of trillions of dollars, right? And when it comes into business, what about the second wave of the quantum machines? To give you just a small example to simplify, if we have, in the chemistry people, I think Dr. Taha and all the attendees or specialized in the chemistry part will understand this better than me. If we do the simulation of 4 atoms of iron with the 4 atoms of sulfur, and we need to do the simulation, we can see the comparison between the classical approximate method. It takes like 8 hours. When it comes into the hybrid approach, because we know it will still quantum computing in a need to supercomputers. So it takes 12 minutes using 77 qubits in the quantum part and 1.5 hours in the supercomputer time. So if you can compare between the time it's taking between these two, definitely this is a significant saving when it comes into time and the energy. The era of quantum utility. And this is a very important slide in my point of view, because this will give you a differentiation between what is quantum utility and what is quantum advantage. What is the difference? IBM in 2023, they announced about the quantum utility. Quantum utility, it's having a quantum machine as one of the solutions side by side by a traditional computer. So you have a problem, you can use a quantum machine to solve this problem, or you can use the classical computers, maybe supercomputers. But in quantum advantage, it means that only using a quantum machine is outperforming, is a cheaper, it's more efficient, more accurate, and more efficient than the classical computer. So this is the quantum advantage. When we have a case and we have a machine that can meet all these criteria, so we can announce that this is the quantum advantage, okay? We don't need, definitely this will not be overnight, because we have a lot of industries, and maybe one of industries outperform and they might reach the quantum advantage before the other industries. So this is not something that will happen overnight. This is keep evolving with all the researchers and the effort of the scientists that working on this area, okay? So this is like a graphic explanation about what I just mentioned. In the utility, you have the problem that can be simulated in both machines, the quantum and classical. However, in the advantage, it's not possible, it's not feasible to run it on the classical machine, and it can only run on the quantum computer, just for illustration, extra illustration. And another comparison between to show you the error or the quantum utility, definitely, as you know, it's a faulty system. The quantum machines are a faulty system, and IBM is working on the error mitigation. And as you can see in this use case, the cost of simulating 40 qubit and measuring the equation using 1024 H100 GPUs from NVIDIA is costing $30 million. On the other hand, if we are running 120 qubit with 3,000 gates, 2023 natural paper has been published, it will cost 4.8K. Definitely, this is a huge difference. This is an efficiency. Despite we have a faulty systems, but we can get results out of it, okay? And this has been proven by a brute force implementation with the UC Berkeley University. We will be able to do this simulation, and we prove that the output from the faulty quantum computer is matching the same results of the classical computers. So this is what I just mentioned. Even the noisy computer that we have as we speak, we can even get some use cases, some implementation, some value out of it. So when it comes into, we are now in 2025, 4 years from now, what will happen? Definitely a lot will happen, okay? So what is the business around the quantum in this area? In 2023, we established the quantum utility. 2026, we are expecting the demonstration of the quantum advantage. 2029, this is the first large scale fault tolerant quantum computer. The fault tolerant quantum computer, which is mean we are getting the full benefits out of the quantum machines, okay? So we could not be able to do it by ourselves. We have to do it together. That's why we have a huge ecosystem around IBM, and the IBM is trying to collaborate with all the institutes, academic startups, and all the communities around the quantum to build a better algorithms to resolve the current problems that we have. So if we can look into the IBM Sterling, which is the latest announcements from IBM by 2029, this is where we will have a fault tolerant quantum machine, where if you want to do the simulation, if we will go back to the basics and the modern laptop, you can simulate using 17 GB RAM and 30 qubit. However, in 48 quantum bits, you need IBM Summit supercomputer to be able to simulate these 48 bits and going beyond that, okay? So the 200 qubit, this will be definitely out of all the computers, the classical computer will not be able to do that. So this is the first large scale fault tolerant quantum computer. IBM just announced it this month, and it will be landed by 2029. These are the three main stations or evolution in IBM quantum journey. If you can see here, by 2025, we had quantum system 2, which is a modular If you can see in this picture, you will have multiple quantum machines working simultaneously together as a cluster. Then you will have, quantum Stirling. This is 200 logical qubits, as I told you. This will give a vision about how many logical qubits we can build with more than 100 million quantum gates. This is very, very huge. And the ultimate goal by 2033 and beyond, we have the Blue Jay, which is 2,000 logical qubits with 1 billion quantum gates. This is a very aggressive roadmap from IBM. And if you look into IBM roadmaps starting from 2016 till now, whenever IBM announces about a roadmap, they are maybe giving a roadmap for 3 years, 5 years in the future, right? Then they expanded the next roadmap. They announced about 10 years from the last year, okay? And now, as you can see, it's 2033 and beyond. This is really a very bold roadmap. There is something is huge in the quantum machine. So if we are talking about the quantum advantage, what is the competitive position from IBM perspective? As we all know, we have different approaches when you are building your quantum machine. We have ion trap, we have spin qubits, neutral atoms, right? But we have 3 aspects that we need to evaluate the quantum system to get the maximum benefits out of it. We need to know the quality, and we should have a scalable machine with the speed, right? But if you look into the natural atoms, it's a little bit slow when it comes into the performance, so it lost the speed. Ion traps, it has a problem in the scalability a little bit. So the conjunction of the speed, quality, and the scale, this is what IBM is working about. That's why you're working with the superconductor. And the most question, or the most frequent question that I'm receiving, why IBM is adapting the superconductor. As IBM, as you know, IBM is a leader when it comes into the hardware, building servers, like the mainframes and all this stuff. IBM has a lot of patents and researchers there. IBM is excelling on the hardware part and the superconductors. That's why they see that this is the proper or the right technology to adapt. So IBM is using the superconductor computers to build and to do the balance between the speed, quality, and the scale. This is on the IDC market size. As you can see, IBM is outperforming out of all the quantum players out of it. I know I'm running out of time in about 30 minutes. I will try to conclude in 1 or 2 minutes. So this is the most important part when it comes into the hardware innovation. Here at the bottom, you can see the evolution of the quantum processors, Nighthawk. We have many versions, but as you can see, we're still starting from the 2016 till the 2025. We have only one single processor working on the system. However, starting from 2016, we can have like multiple chips or quantum processors working simultaneously as a one unit. Definitely, this will serve in quantum system 2, where you have multiple or cluster of quantum computers working together. Imagine how powerful this machine will be. So IBM is supporting the partners when it comes into technology. As you can see, this is a simple way of working with IBM quantum systems on the cloud. So the enterprise or the client is working with APIs, which is communicating with the Qiskit runtime. And this is the Qiskit runtime service, whether you can run the Qiskit runtime in a quantum data center or a dedicated system for you. And this is IBM Quantum System 2, as we mentioned. Quantum System 1, it was one processor, one chip, working slowly, isolated. And Quantum System 2, we have a cluster of quantum systems. IBM is offering many plans to support the enterprises, ecosystems, and the academics as well. We have many plans. I will not dig deep into this. It's more into commercial part. But the most important part is the quantum accelerator. This is for the big enterprises. IBM is joining the enterprise with the researchers in any enterprise, and together IBM researchers and the quantum team on this enterprise working together to identify use case, develop algorithms, identify the proper resolution for this algorithm, conducting POC, or building an intellectual property or IP to be registered by the client itself. So this is the most important program in IBM. It's offering even a training to bring the quantum team up to speed. I will not, because of the time, this is one of the important announcements. Now IBM has a Qiskit code assistant, and this is the AI part where it can help, IBM can help the developer to build more algorithms in a faster way. It can help him give some code snippets, enhancements, and all this stuff. And the code assistant is available for the premium users. Last one, the quantum and AI. Definitely, we believe that the AI is a game changer, and that's why IBM is focusing to identify the proper use cases for having the artificial intelligence working to build machine learning algorithms can run in the quantum machines. These are the two main areas that IBM is focusing on. AI enhancing transpiler, where it can enhance the way that you execute your algorithms in the quantum circuit. It will help the developer to reduce the complexity of the circuit and select the proper qubit route. And as I mentioned, the Qiskit code assistant, where it will help the user to build his own program in a proper way, faster way, error-free. And this is using IBM Granite, which is a generative large language model developed by IBM. Definitely the applications, I will not talk a lot about it, but it's across all the industries. There is no time to mention about it all. But what I want to mention, we have the use cases. We have a lot of industries that can get benefits out of the quantum machines. We have a talent gap because, as you can see, the ecosystem is still under exploration from the giant vendors and even from the client side. So we don't have enough people who work on this domain. That's why we have all these communities and the awareness to spread it across the globe to enable more people on this technology. And if definitely the hardware access, when it comes into commercializing and achieving the quantum advantage, definitely the demand will be high. Like the demand on the GPU, as we know now, it's very challenging, and you will see the same on the hardware access. That's why we need to act now to build the communities, exchange the experiences, and build the proper algorithm for the proper use cases. So by that, I want to conclude the presentation. I didn't talk about the ecosystem of Saudi Arabia, of the Gulf, but what I want to mention about it, the people start moving, they realize the quantum advantage here in Saudi Arabia, even in the Gulf areas, in Qatar, in Emirates. People start identifying some use cases, working on it, building communities, even supported by the government. I don't have many information to disclose because a lot of it related to some government entities, but what I'm telling you that we have open communities here in Saudi Arabia working on the enablement of the young people here in Saudi. And there is a government activities that is being done by the government entity and sponsored by the government to build a quantum community and be a leader in the quantum area. Thank you for your time. Definitely, I make it a little bit long, but I hope that you get benefits out of after this session. Thank you.
Thanks very much, Imjad Ahmed. Thanks very much, Ahmed, for this nice and informative and clear presentation as well that covered a lot of aspects about IBM, but not only confined to IBM, but the quantum computing in general, from the development phase to the industry, to the use cases, to the adaptability and the commercially having a commercial viable platforms. So yeah, thanks a lot for this. So with that, opening the questions, the Q&A session. So please feel free to post your questions in the chat. So we have here two questions from Ala. So and Ala has the first question is was asking about the sample-based quantum diagonalization, and I believe this question will be directed to Yusra. So hopefully Yusra is there with us. Yeah.
Yes, I'm still here. I have to leave in a while, so just answer the question of Alan. Thank you so much, Alan, for the question. So you asked what about sample-based quantum diagonalization, SQD and QKD? So these are like two algorithms that have been used widely in like quantum machine learning and quantum optimization. They are not frameworks, but they are algorithms that can be fully implemented on Qiskit SDK. So the main idea behind these algorithms is the fact that we can estimate the eigenvalues and the eigenstates of our Hamiltonian in a way where we don't really require building in depth like quantum circuits. So I hope I answered your question. So this is like these are like widely used algorithms in several use cases, but they are more like designed for NISQ era devices as well, because we don't need to go in when it comes to phase estimation or number of
ايوه
the algorithm itself.
في حد اتصل بيا
So yeah, I hope I answered your questions.
Thanks, Yusra, for the answer. And also, this is also a newly developed algorithm. So Ala has another question about curl of quantum diagonalization lattice Hamiltonians. Also, he's asking about it, and he's mentioning the link for the tutorial associated with this algorithm. What's your thoughts about it?
Yeah, same thing. So it's both algorithms are somehow similar. So they're both algorithms, both they can be implemented on Qiskit, and both they deal with eigenvalues and eigenstates. So the first one is like for general Hamiltonians, the second one is for lattice Hamiltonians. Yeah, and both are designed for the NISQ era devices. So you can implement them. For now, like most of the implementations I saw for these algorithms are on Qiskit and not on Penny. So yeah. They are gate-based algorithms. So I hope like I answered your questions. I just like gave you like a small overview about like these two algorithms, but they are widely used. Yeah, there are several algorithms that I didn't mention, so I selected only like few algorithms in machine learning optimization. There are plenty. There are like several models, QUBOs, and different architectures. So scientists are like playing with the different architectures, moving things around and creating new algorithms everywhere. And that's why we wanted to present that software. As Dr. Ahmed said, like the software is just evolving and evolving every day.
Yeah, thanks very much, Yusra. And by the way, we are also working in Molkit, also Alan and I, with several collaborations on using this sample-based the quantum algorithm. So we have now potential use cases in chemistry we are working on, and we are trying several things related to quantum machine learning to interpolate potential energy surfaces, and also now experimenting. And this is in our pipeline to experiment with SQD for several and other similar algorithms for several use cases in chemistry and computing spectra and so on. So thanks very much for highlighting this. So a question for you. If you choose best quantum SDK to work on, what it will be and why?
Well, I cannot say best SDK because it depends on the application. So if it comes to machine learning, I think PennyLane is widely used. You can do a lot with PennyLane. When it comes to optimization, I'm more with D-Wave or Titan-Q of Infinity Q. These SDKs I use the most, but I cannot say they are the best and I cannot say they are the worst. So this is like just because of I found them useful for the use case that I'm dealing with right now. So it depends. There are several SDKs out there in the literature, so it's on you to choose the best SDK that you can use for your specific use case. Yeah, so I gathered like the widely used ones that you can use for your work, but it's still like أنا متحفظة. I don't have a preference. It depends on the use case.
Yeah, indeed. Yeah, that was a question just to get your taste about these things. So for Ahmed, his slide now. Thanks very much, Ahmed, for being willing to share your slides. So we are gonna have a Google directory for this, and just please feel free to drop your slides as PDF there or any format that you would like, and then we are gonna distribute this link among the attendees of this fifth edition of the monthly series. We have a question for Ahmed. What are the KPI for IBM concern in apps like NLP, image processing, neural networks, big data domain, and so on?
Okay, this is a very tricky one because when it comes into developing the quantum machine and related to the data processing, we have a lot of measurement when it comes into scale, how we can run these algorithms on the scale, how many use cases that we can implement. The problem when it comes into having a large data set, it's a little bit tricky. IBM is working in a way that we have internal or let me say like some confidential measurements inside the IBM to be able to have a productive, let's say, measurements when it comes into these use cases. If you saw this slide related to the competitive, let me bring it to the picture. Let me here bring it to and share it here. Let me share the entire screen. Can you see my screen?
Yes.
Yes.
These are the 3 dimensions that we are working on: the speed, the quality, and the scale. Okay. So when it comes into the data processing, we still, as an IBM, we have challenging when it comes into processing large number of data, and we still believe that the hybrid approach is a proper way to handle such use cases. If you will look into the roadmap, you will find one of the objectives is a dynamic circuit, something called dynamic circuit, which will enable the quantum machine to be able to get a feedback or a retry mechanism. Okay, when it comes into the execution, because as you know, it's the quantum algorithms execution. It will be straightforward. You don't have a loop. You cannot go back, right? Because the quantum system will collapse, right? So that's why IBM developed this dynamic circuit where we will be able to do like get a feedback and get the results and do like a retry using a new set of data. So this is on high level how IBM is handling such mechanism. And these are the 3 dimensions that IBM is measuring when it comes into the quantum computer, when it comes into the performance. I hope I answered your question.
Okay, thank you.
Yeah, thanks very much, Ahmed. So for everyone, please feel free to ask your question now. Also for Dr. Ahmed Shawqi Musa, if you have a question or anything, please drop it in the chat. Yeah, so for the hackathon, please contact William Slater. Perhaps, William, you would like to say some words about it?
Sure. this is going to be a different kind of hackathon, and I'm saying this from the experience of having participated. This will be a different kind of hackathon. I'm saying it from the experience of having participated in hackathons myself. I participated in a blockchain hackathon back in 2018, and you basically just beat your head against the wall. It's horrible. You know, you start Friday night and you end up Sunday afternoon, and you're sleep deprived, and you don't feel so good after the hackathon. So we're turning this into a 30-day hackathon, and we will be asking for mentors. And if people need assistance or professional advice, they can go get that. There will be 3 cash awards. First place will be $5,000. Second place will be $3,000, and third place will be $1,000. And we believe this will make a considerable impact in the quantum community. And I believe it's not about the money. I believe it's about advancing the state of the art in the quantum community. So I think everybody that participates will be a winner.
Yeah, so thanks very much, William, for the information and also the clear announcement about your beautiful hackathon, and also the detailed plan about it. So hopefully more people will join and help indeed. So are there any other questions? This is the last chance to ask. Okay, so if not, then I will be happy to conclude the session. So thanks everyone for attending today. Special thanks for our esteemed speakers, and also all of the nice talks that they have presented today. Dr. Ahmed Shawqi Musa, Dr. Muhammad Zidan, Dr. Muhammad Amin, and also Yusra Farhani, and also Engine Ahmed Salim for these beautiful talks. And special thanks also for William for mentioning the hackathon, and special thanks for all attendees who asked very valuable questions today. We got a comment from Zain Gad that he wasn't able to follow up with all details, but that was an eye-opening for him, the session. So thanks everyone, and thanks for all of these nice discussions. Please feel free to watch the recording on iCafé YouTube channel. And by the way, there is also a future video on my own channel that we are going to talk about this, the physics limitation of quantum hardware. William, please.
Yes, I just want to let everybody know on the call that I sometimes people think that we're separated by ethnicities or by countries or whatever. I just want everybody to know on the call that last month my wife and I had a chance to meet with Dr. Taha Salim with his beautiful wife in Amsterdam as we were wrapping up a trip, and he's just like a brother. It was a wonderful meeting, and you know, people look at lines on maps and flags and stuff like this. We are all quantum brothers and sisters, and we're all one quantum community. So I just wanted people to know that, you know, it's not me in the U.S., it's not you in Egypt or wherever you're at. You know, we are all one quantum community, and I think Dr. Taha, he's a wonderful man, and I'm just grateful to be part of y'all's group.
Yeah, thanks very much, William. We have enjoyed your company. You are a very wonderful person as well, and you have so much also to learn from. And a special thanks also to your wife. She is wonderful as well. So that was a great indeed meeting and dinner. So thanks everyone, and please feel free to watch the recording. And next time is gonna be, we have the quantum education, but also are going to have a quantum summer school. Also, Ella and I, from our side, we are working on some hands-on And there will be also some technical talks to introduce the chemistry applications, but also the encryption. And so stay tuned with our announcement about the summer school at the end of August, and also the tryout hackathon at the end of July, and the next monthly series in July and in August. And we are looking forward to host all of you in the hackathon in September. And also feel free to volunteer to be judge if you'd like, if you don't have budget to travel, or we cover your travel as well. Feel free also to volunteer as an online jury member, and this will also serve to be a very good viable addition to our community. So thank you all, and wish you a nice day and nice evening, and looking forward to see you in the upcoming events as well. Yeah, thanks everyone.
Thank you.
Yeah,
Bye-bye.
Okay, bye-bye.